SIGDIAL's 2020 special session on situated dialogue with virtual agents and robot. This is the second version of RoboDial. I'm Jose from Hierarchical University. I'm one of the organizers of this workshop. The other organizers are Stephanie, Matt, Vikram, Matthias, Casey, and Cynthia. The reason why we proposed this workshop is kind of a follow-up to a series of successful workshops at other major venues where the topic of situated interaction with dialogue is being addressed. Just to give you a few examples, I think Robot NLP was one of them in the last edition of NACL. And we also had the first edition of RoboDial in SIGDIAL 2018. What we've seen in the last years is that dialogue is also moving into physical spaces and virtual spaces using augmented and virtual reality. And it often has an embodiment such as a robot or an agent. And this changes a little bit the way we have been doing research on dialogue lately. Since this often relies on very large data sets and the use of machine learning, which is often not the case for this kind of domains where there are very specific needs. The data sets are very small, and there's also some requirements of the task, such as it has to be trustworthy and robust. And we often cannot guarantee that with the current machine learning approaches. Another issue is that it's not always clear how to evaluate the quality of the dialogues. We're not just trying to replicate the dialogue that we have on the training set. So it's not really about competing for the best state of the art or the best accuracy or the best metric. It's delivering something different, and it's not so much about leaderboards. And then therefore, we are proposing this workshop to bring together people that work on situated and grounding natural language processing, also people working on HRI, and naturally the dialogue community present here at SIGDIAL, to think about the problems that we have and hopefully inspired by the program, come up with a few ideas to move the field forward. For this year's program, we received 8 submissions. 4 of them are accepted as full papers and will be presented orally as a regular SIGDIAL paper submission. These papers, they cover a range of topics such as turn-taking, grounding, learning, reasoning, and also navigation tasks, and also the way that the robots should address the non-verbal communication part of the interaction with these robots and agents. We have 2 additional demo papers that will be presented as well. And they cover mostly things like multimodality, which is also very relevant, and also particularly physically situated dialogue. And finally, in a later stage, we have invited contributions for late-breaking reports and position papers, which include also the topics such as multimodality, grounding, learning, which are of course very relevant for physically situated interaction. Just a brief summary of what is expecting us in the next couple of hours. We will start with the talks from the papers accepted to the conference. After that, we have a live Q&A session for the demos, where we'll be able to see how demos work and also to ask questions to the authors. We will go back to the papers in the first part of the sessions, where we'll have the live QA with the authors, and to the end we have the presentations from the position papers, followed by the live QA with the authors as well. So this is what expects us in this year's RoboDial. We do think that's an exciting program. We hope that you get some inspiration from it. Do feel free to go to the website and check the more details about the workshop. I wish you all a good session and a great conference. Thank you.
Hi, my name is Felix Gervitz. I'm a brand new postdoc with the Army Research Lab, and formerly I was a grad student at Tufts University in the Human-Robot Interaction Lab. So I'm going to be talking today about some work I did at the end of my grad career. So the title here is It's About Time, Turn Entry Timing for Situated Human-Robot Dialogue. So as a main motivation here, we know that humans are really good at exchanging turns in conversation. We can do this really quickly on the order of a few hundred milliseconds. And it's thought that we mainly do this by using a variety of cues to predict a turn, an ongoing turn, and then plan our turn while the person is talking. So it's thought that we use lexicosyntactic cues primarily, among other cues as well. So that's what we're going to focus on in this talk. And current dialogue systems, they really don't have this capability apart from a few research prototypes. But this kind of fluid turn-taking can benefit systems in a variety of ways, including improved response latency, which could lead to more natural interactions. It could support a wide range of overlap behaviors, including supportive ones, such as back-channel feedback or collaborative completions. And for situated agents that interact in an environment, aka robots, it can allow actions to be initiated early, or what we call preemptive action execution, which could save time. So to support this kind of fluid turn-taking, we're developing a computational framework. So the first part of the framework here is a model that can make incremental predictions about an ongoing utterance. So if it gets the input, go to, it might predict either go to the kitchen, go to the bedroom, etc. And to inform this, we use contextual information to bias the predictions. And this could include stuff about the perceptual context, the task knowledge, the dialogue history, etc. And we also have a turn entry manager component, which gets information from the utterance prediction component, estimates the duration of the prediction, and then uses that to compute these different entry points and to determine when a system could take a turn. So this is all integrated into a robotic architecture, specifically the diarch architecture, and we evaluate this on a corpus of human-robot dialogue. So the utterance prediction component, we use a bigram language model to generate these predictions. There are other ways you could do this, but this is a simple, quick way, and that represents some of the kind of information that we care about. So here's a quick example of how this works for an input word, go, and let's say we're in the context kitchen. So it basically generates this tree for every input word that comes into the system and generates these full utterance predictions. So here you can see that go to the kitchen was the top prediction that was made here. And that was largely because the bigram the kitchen was heavily biased because we're in the context kitchen. So there's more detail in the paper, but that's kind of a general overview of how the prediction model works. Before I discuss the turn entry management algorithm, I want to make a brief note about the different entry points that the system could come in. So a lot of this is based on the work by Gail Jefferson in conversation analysis. She studied speech overlap. So we're going to ignore these first two types of overlap because they're more accidental. These have to do with simultaneous startup. But the first kind of overlap we're going to discuss is interjacent overlap. So this occurs kind of when somebody comes in about midway through the utterance, not near a transition point. Usually this is done to clarify or repair a problematic utterance, or to just express uncertainty about what was said. There's also a last item overlap, which is any overlap that occurs at the last word or last lexical item of a turn. And this is not intrusive. Usually it's done to kind of transition the turns very smoothly without any kind of gap. And then finally, TRP entry, which is not overlap at all. This is entry at the transition relevance place, or the transition point between turns. This is kind of the ideal point that we mostly want the system to come in. So now onto the turn entry management. This is a component we have that's situated in the dialogue manager of the architecture. It's largely an algorithm that we developed. The way that it works is, again, there's more detail in the paper. I'm just going to kind of gloss over this. But basically, for every word that comes in, we generate a full utterance prediction of that word. And then we compute these different entry points that I just showed in the previous slide. So for the TRP entry, we get the start time of the utterance. We add an estimated duration, which we compute using the syllable count of the full utterance. And then we multiply each syllable by 180 milliseconds. This is the average syllable duration in the switchboard corpus. It's a very kind of crude way of getting the utterance duration, but it seems to be pretty effective. And then we take into account the text-to-speech delay as well. So in this way, we compute the different entry points. We also simulate the actions because, again, this is for situated agents. A lot of times the utterances are commands or instructions to perform some kind of action. So we need to know if the action will succeed or not. So we do this by checking the preconditions of the action. And if the preconditions fail, we generate a failure explanation right away. This will usually be an interjacent overlap, something like, sorry, I can't do that. And in the case that the action will succeed, we set the response type. We have a policy here to determine when the system should come in and when it should take the action. So our simple policy is that it'll just come in at the TRP basically every time, although we can change this to produce overlap if we need. And we also have it perform the action as early as possible, although again, we can delay that if necessary. And finally, we have a separate process here to determine when the response should actually come. So in the case of a TRP entry, we want to basically wait until that TRP entry point has been reached. And then as soon as it's reached, we initiate the response. And since we took into account the text-to-speech delay already, ideally, the system should come in right at the TRP. So in terms of the architectural integration, this is a configuration of the DIARC, Cognitive Robotic Architecture. It looks very familiar, I'm sure, to anybody who's worked with dialogue systems. And as an example of an utterance in our framework, like running through the architecture here, let's say we have the word go come in at t equals 0. This comes into the speech recognizer, just a single word. The utterance prediction component, let's say it generates the full prediction, go to the kitchen. Although in many cases, it'll take multiple words before a prediction is generated that is above threshold. But it gets go to the kitchen as text. That is sent to the semantic parser or the NLU component, which converts that into a logical predicate. And then that is sent to the dialogue manager, which contains the turn entry management algorithm. And that computes all these different values, including the duration, the different entry points, and then the action and the response associated with that command. So in order to evaluate this, we tested we ran 96 utterances from the hierarchical corpus, which is the human-robot interaction corpus. And it's basically a very small corpus of simple commands to a household robot. So things like go to the kitchen, grab the bottle on the table, these kind of commands. And we use text input as opposed to speech. The reason we did this was to avoid some of the noise associated with speech input, kind of abstract away some of that. So we kind of simulated incremental speech input using text. So we used, basically we set a timing for each of the syllables coming in to be 180 milliseconds, just like in the algorithm. And I'll discuss at the end a little bit about some of the limitations of doing it that way. In terms of our primary measure, we used the floor transfer offset, or FTO. And this is basically just the difference in time between the start of the second turn and the end of the first turn. So an FTO of 0 here means that there was a fluid transition. A positive FTO means that there was a gap, and a negative FTO means that there was overlap. And our main hypothesis was that the framework would support accurate TRP entry, so FTO would be close to 0. It would also support early actions and interjacent overlap, especially compared to a non-incremental baseline system. So in terms of the results, we found fairly accurate, the prediction model was fairly accurate at about 71%, and the predictions themselves were made about halfway into an utterance on average. So we did find that the framework led to smaller FTOs compared to the non-incremental system. And the non-incremental system was just the DIARC architecture without any of the components we added and without incrementality. So you can see on the histogram here, part B, this is the distribution of FTOs for the 68 utterances that the system correctly predicted. And you can see that it was about 1.4 seconds, or 1400 milliseconds was about the average entry time. So this is pretty consistent with other non-incremental systems. And up here in A, you can see our system came in basically right around 0. So the mean FTO was negative 1.1. So, and not surprisingly, the difference here is statistically significant. We also found that the framework supports interjacent overlap, specifically for the 15 predictions that were unactionable. There was no action corresponding to them. The system came in about 680 milliseconds before the transition point, before the end of the utterance. And in some cases, you can see it even came in to over 2 seconds early, depending on how early it made the prediction. We also found preemptive action execution, where the earliest action started about 635 milliseconds into an utterance, like on average across all of the trials. So this represents very early actions. Here's a demo video I'm going to show you where we got this running on a PR2 robot using speech input. And here is a comparison between the non-incremental system and the incremental one. So here's our baseline system.
Can you please drop the apple on the kitchen table?
So you can see there was a bit of a delay there. Here's our prediction model.
Can you please drop the apple on the kitchen table?
So this is when it tried to come in at the TRP, and you can see that it was a lot more fluid than the previous one. Here's the baseline system when it can't do an action because the preconditions aren't met.
Can you please drop the apple on the kitchen table?
I cannot release apple because I am not dressed in anything.
And here's the same example with our prediction system coming in early.
Can you please drop the apple on the kitchen
I
table?
cannot do that because I am not dressed in anything.
Okay, so that shows the interjacent overlap. And finally, here's the last item overlap with our system.
Can you please drop the apple on the kitchen table?
Okay, so very quickly, the main limitation here, I think, is in the evaluation, where we used text input and we had a fixed word duration estimate. So obviously that's not going to be the case with real speech. So to kind of demonstrate this, we did a small supplementary evaluation, still using text input, but we used a variable duration for each syllable. So now instead of being fixed at 180 milliseconds, it was now a random number between 100 and 200 milliseconds. And the algorithm also computed a random number as well for its estimate. And we actually found good performance here. We still found an FTO very close to 0. In this case, it was negative 16.5 with an acceptable range of performance. So thank you for listening to my talk. Here's my contact information if you have any questions.
Hello, my name is David McNeil, and this is the conference paper, Learning Word Groundings from Humans, facilitated by Robot Emotional Displays. This paper was completed with the assistance of my advisor, Casey Kennington, as part of our research for his Speech, Language, and Interactive Machines group within Boise State's Computer Science Department. According to Charles Fillmore's Pragmatics and the Description of Discourse, humans first learn language by engaging in spoken dialogue with other humans. If we want to model this natural language acquisition behavior using a robot, we must confront the obvious paradox. Who talks first, and how do they make themselves understood? For this paper, we test the hypothesis that emotional displays are a viable solution to this cold start problem. That is, if a robot needs to communicate with a human, but doesn't have any experience with language, emotional displays are an appropriate method for communicating the robot state to its human dialogue partner. We tested this hypothesis in a live interactive study in which 21 participants were tasked with teaching our robot different words by using visual references in 2 back-to-back trials. One in which the robot used emotional displays, and a second in which the robot did not. What words the participants taught and what objects they used as references was left entirely up to them. In addition, the robot was programmed to operate autonomously without the direct control of the researcher, who was only present as an observer in case the participant needed limited coaching or any part of the system broke. To mitigate learning effects between the first and second trial, the order in which the robot used emotional displays was alternated. Let's step backwards for a moment to interrogate our hypothesis. Why use emotional displays at all? Emotional displays are a viable solution to an initial lack of language information because emotional displays can relate the robot state to its human teacher. And emotional displays are developmentally appropriate for the most common language acquisition setting, an adult teaching a child, and would not lead a human user to make incorrect assumptions regarding the robot's comprehension. For the purposes of this study, we restricted Cosmo's emotional displays to only include those with which a previous group study of participants had determined most clearly communicated understanding or confusion. We drew inspiration for our language learning system from various sources. We've already addressed our choice of setting, but for the robot's grounded semantic model, we rely on the words as classifiers model, which can accurately classify words after only a few visual examples. This would work for a limited interaction such as the one in this study. We used the Anki Cosmo robot according to prior work done by our SLIM research group that showed users treat Cosmo like it is the right age for a language learning task, and also found the robot engaging, all characteristics necessary if we want to enlist casual users as language teachers. That left several questions regarding how the robot was to interact with its world and with users themselves. How could the robot indicate to the user what it was looking at? And how should the robot behave outside of emotional displays to indicate to a user that it required more information from them, either in the form of more words or yes-no feedback to its own word proposals? To address these questions, we programmed Cosmo to alternate between object and user-oriented behavior, either gesturing with its wheels and lift to the object it was capturing, or creating eye contact with the user by locating their face. Interspersed with these two behaviors were constant, small, randomized movements that would demonstrate to the user that the robot was still active while its language models were training, or it was running images from its camera through its object detection module, which was the bottleneck for our system. The system we engineered for the study is outlined here according to its various modules on the left and the separate goals those modules were trying to achieve on the right. The modules are arranged hierarchically. That is to say, some tasks can only be addressed after previous modules have already completed their own goal. For example, in order for Cosmo to ground a word, it must first locate objects and navigate toward them. To do this, the visual perception module first handles the event of a new image being captured by Cosmo's camera. It passes this image to the object detection module, where a pre-trained graph taken from the TensorFlow library outputs bounding boxes around the objects. We take the bounding box that has the greatest probability of containing an object, as the learner's attention is assumed to only be focused on one object at a time. We crop the image according to the bounding box dimensions and submit this as input to a Keras implementation of an image classification neural network, trained on ImageNet corpus weights. The second to last layer of this trained network becomes the feature representation of the object, which will be used to train the classifiers of the grounded semantics module later on. First, before that, the automatic speech recognition module parses transcribed user speech, classifying detected speech into either words heard from the user, positive feedback affirming the robot's most recent action, or negative feedback doing the opposite. Those heard words will be taken and used as labels for the grounded semantics module. These labels, combined with the object features from earlier on, are used to train separate classifiers for each word, using those images that are deemed relevant for that word. Words are assumed to refer to an object if it is heard less than 10 seconds after the object was seen. This time period was chosen after a period of trial and error spent testing the robot with real users and considering the lag introduced to its interaction by the ASR, object detection, and feature extraction models. The largest square area outside of the bounding box in the image is used as a negative example to train that word's classifier. This design, in which each word acts as its own classifier, trained on positive and negative visual examples, is known as the, quote, Words as Classifiers design, or WAC. It looks something like this. The graphs in the center column represent every word that Cosmo has heard and has trained a classifier for, after processing at least 3 images of an object within a 10-second window after the participant has said that word. Once Cosmo possesses a trained classifier for a word, that robot will use the classifier among all the trained classifiers in its vocabulary to determine which word best fits a new object. This best fit word, which in the case of this graphic is the word yellow, will be proposed by the robot to the participant to describe that object. At this time, positive and negative feedback from the participant will be interpreted as a command to either destroy the classifier for the proposed word and start again from scratch, if the feedback is negative, or to add this new feature data to the proposed word's classifier, if the feedback is positive. In order to engage the participant into supplying these word labels and feedbacks to the robot's word proposals, the robot follows a rule-based pattern for shifting its attention between the world and the user's face, indicating through various small randomized gestures that it has either seen an object, is looking for an object, or is looking for their face. In those trials when the robot can perform emotional displays, those displays occur after the robot has proposed a word and it has received feedback from the user. We evaluate the robot's performance in the task based on the number of words it hears from the participant, the total instances of positive feedback it hears, and the total instances of negative feedback it hears. The more total words and total feedbacks, the better, as this indicates the user is more engaged and supplying more and more accurate information by which to train Cosmo's grounded semantic classifiers. We also evaluate the robot based on survey responses written by the study participants following both of their trials in the study. These task-specific questions are prepended to the standard Godspeed questionnaire. This chart shows the mean number of inputs given to the robot along with the standard deviation and the relative influence of learning effects from the first trial to the second for the study participants. Between the first and second trial, the lower standard deviation is bolded and the higher mean value is bolded. The number of positive feedbacks increased significantly from the first trial to the second, perhaps affected by user engagement with the Cosmo Robot, which surveys showed increased slightly over time, along with general positive measures of the robot. The wide variation in the number of inputs provided to the robot between participants perhaps indicates the relative unintuitiveness of this robot language learning system for a human user who has been given very limited instructions on how to teach it. This chart shows the same measures, but influenced by the presence of emotional displays rather than trial order. The number of words said aloud by the human user and detected by the robot's ASR increased with the presence of emotional displays, along with the number of positive feedbacks. However, taking into consideration the significant amount of variation between users, a wider study would need to be done to validate these increases. This chart shows the correlations between participants' survey responses and those trials in which the robot performed emotional displays. Interestingly, there were correlations to robot emotional displays and participants' estimations of elegant movement, as well as the robot they deemed to be nice and interesting to work with. The higher p-values, however, indicate a need for further trials to corroborate that these correlations were related to the presence of emotional displays and not simply the design of the Cosmo Robot itself. Looking at the user surveys, we find that trial order has a limited effect on participants' engagement in the task. Interestingly, participants were slightly more engaged by the second trial, perhaps after becoming more accustomed to the task setting and the robot system. The presence of emotional displays likewise has a slight effect on participants' engagement. The drift of participants' ratings to either extreme is interesting, as it may indicate that the presence of robot emotional displays is confirming participants' views of themselves in the teacher role, leading to increased engagement from those participants who believe they are successful and decreased engagement from participants who do not. In looking at participant perceptions of the robot's intelligence, we find that trial order did not have a significant effect. Participants' ratings skewed toward unintelligent across both trials, confirming our prior research that shows that users treat the Cosmo Robot appropriately for a language learning task. However, with the addition of robot emotional displays to the language learning task, participants' perceptions of the robot's intelligence moved to a bimodal distribution, with more users saying the robot appeared either slightly intelligent or slightly unintelligent. Again, emotional displays appeared to cause a greater polarization in participant scores of intelligence, as it had with participant estimations of their own engagement. Whether this was due to participants' own pre-existing beliefs regarding their competency as teachers or as users of technology in general would need further research to determine. Robot emotional displays caused an increase in the number of inputs provided to the robot, which was positive for semantic grounding, as well as a wider variation in the number of inputs, which was worth exploring. The wider variation in inputs may be indicative of the complexity of this task for a casual human user who is being given very limited open-ended instruction, or it could indicate that emotional displays may be too ambiguous for the purposes of the language learning task, and that, rather than clarifying the robot's internal state, may only be translating a form of human attribution bias into a human-robot interaction. In order to clarify this distinction, more research remains to be done, with an increased focus on viewers' perceptions of themselves and leveraging other, less ambiguous means of making the robot's state more apparent to the human user. Thank you.
Hello everyone, I'm Keting Wu. Today I'm going to introduce our work on learning and reasoning for robot dialogue and language tasks. This work was conducted when I'm studying at the USTC. It is guided by Professor Shiqi Peter Stone and Xiaobin Chen. Xiaobin Chen is also my advisor. Today I will introduce our work from 4 aspects. First, I will give a brief introduction and background of our work. Then I will introduce our approach. After that, I will show some results to support our claim. Finally, I conclude this work. So let's start with the first part. In this work, we aimed to solve an indoor delivery problem on a service robot. So here is our task's definition. Consider an indoor scenario. A robot first needs to dialogue with people to find out the delivery task's goal location, which is called a dialogue task. And then it takes navigation tasks to complete the delivery task, which we call navigation task. The figure shows our lab's robot Kejia, and all the experience of this work was conducted using Kejia robot. So, how to complete this kind of tasks? One popular way is knowledge representation and reasoning, where our objective is to concisely represent with declaratory knowledge and robustly reason with it. Here I briefly introduce two methods of KR. One is ASP and another is PLOG, which extends ASP to support probabilistic reasoning. ASP usually consists of a set of logical rules. Each rule has two components called head and body, and all rules can be read as if body is true, we can infer that head is true. As for PLOG, besides ASP rules, it has probabilistic rules. Take the example shown. It reads, if B holds, the probability of A, T equals to Y is B. In this work, we have chosen PLOG for its probabilistic reasoning, and here we take a navigation task as an example to show how PLOG represents knowledge. The first example represents the probability of location at grid X, Y being occupied is 50%, and the second example says if door A is open, the location at the grid X, Y is not occupied, which means the robot can go through it. So, in this way, we can define many rules to describe a nearly perfect world model of a certain task. However, the knowledge doesn't change all the time and cannot respond to external changes. So to respond to external changes, we need another skill. Here we choose reinforcement learning since it's powerful learning ability. Even though environment changes, reinforcement learning usually maximizes the long-term rewards, and a reinforcement learning program often needs to define some basic components. For example, it needs to define state, which is the internal representation of an agent. An action means an agent's behavior, and after an agent has done something, it will receive feedback of the environment, which is a reward. Sometimes we will also define the transition function, which describes how the environment will change after receiving the agent's action. If agent needs to learn its translation function, we call it model-based reinforcement learning. Otherwise, it is model-free reinforcement learning. Again, we take a navigation task as an example to show how model-based RL works. First, agent will be told to reach a target location, and then it will use its current policy to try to reach the target location. Usually, it needs to try many times. After trying, the agent gathers experience from environment and uses the experience to update its world model. Then agent will update its policy based on a new world model and try the next task, until agent's world model and policy convergence. Now let's make a brief comparison between KR and model-based RL, or MBRL. KR is strong in representing and reasoning with knowledge in a variety of forms, where MBRL is relatively weak. However, MBRL is strong in learning from interaction experience, where KR is relatively weak. Based on this observation, we have a natural idea that we can combine both advantages. That is, KR can give MBRL an initial world model to help MBRL generates a powerful initial policy, and then accelerate its learning. In turn, after MBRL learns, It can provide the quantitative knowledge of the word model to update KRR's probabilistic rules. So that is what we have done. Next, I will introduce our framework. We can see the knowledge of KRR comes from two sources. One is human design and another is NBIL. Human usually could give common sense knowledge, and NBIL can give mainly quantitative knowledge, which usually dynamically changes. Once KRR updates its knowledge, it can use the latest one to complete the next task. Here we briefly show the characteristics of KRIL. KRIL acquires declaratory knowledge from human or probabilistic knowledge from model-based IL, and it dynamically constructs a partition word model. Next, we show how KRIL works in practice. We consider two states of a robot, free or not. When the robot is free, it randomly selects a task. Here is a navigation task, to try to complete it and update its knowledge base. Once it receives a task, it first uses related knowledge to initialize the NBIL's word model and then tries to complete the task. Now let's discuss the advantage of our KRIL. We know that if the knowledge of KRR is more complete, it is more useful to initialize the word model of NBIL. For example, we should add such as time, weather, and all other related factors into state space. Because if the robot knows how now it is sunny morning, it should keep away from east-facing windows. If it uses lesser sensors. However, including these factors will enlarge the state space quickly. So, rather than directly including all factors, KRIL computes action policies accounting for a larger number of domain variables by knowledge representation and reasoning. So KRIL retains both model scalability and computation feasibility. Next, we first introduce our experiment settings and then report our results. Our experiment map was generated using Cosmo Robot. A real office domain includes 5 rooms, 1 shop, and 4 blocking areas. All deliveries are from the shop and to one of the rooms. Here is our definition of our delivery task. It includes 2 subtasks. One is dialog system for specifying service requests and another is navigation for physically delivering objects. Delivery task specifies 5 roles, 2 persons, and 3 items, resulting in 30 possible service requests. Here is an example to explain. First, the robot talks with a person to get the request. After the robot confirms, it started to navigate to the target location of request. Here is the specific information of 2 subtasks. For navigation tasks, we use RMAX to learn word models and action policies, and in all tasks the robot starts from the shop rule. As for dialog tasks, we model dialog manager as POM-TB, and it has 2 state spaces and 2 action types. If the robot finally completes the delivery task, it receives a big reward for the dialog task. Otherwise, a big penalty is given. Next, we show the results of our experiments. The first result is interesting. We found that the knowledge from the navigation task can be used to help the robot dialog task. Specifically, we collect the amount of information in terms of belief entropy needed by a robot before it conducts a delivery task. The results show when difficulty grows, a robot needs to collect more information from dialog before conducting a delivery task. Here, the higher value of BR, the higher the probability to block a robot move. We also compare the KRIL and a baseline on the delivery tasks, and it shows KRIL improves the quality of policy and outperforms the baseline in all blocking rate settings. It says a real-time update mode model is important for tasks. If you are interested in other experimental results, please refer to our paper. Now finally, we conclude our work. First, we developed a KRIL framework that integrates computational paradigms of logical probabilistic knowledge representation and reasoning, and model-based reinforcement learning. Results on delivery tasks suggest that the learned knowledge from RL can be represented and used for reasoning by the KRI component, enabling the robot to dynamically generate task-oriented action policies. Thanks for watching the video. If you have any question about this work, please do not hesitate to contact me or co-authors of this paper.
An attentive listening system with Android Hierarchical, comparison of autonomous and voice interactions. I'm Koji Inoue from Kyoto University. Our research group has developed an autonomous Android robot which is named Hierarchical. As you can see here, Hierarchical has a human-like appearance. So human-like natural dialogue is expected for her. So far, we have considered several dialogue tasks. For example, job interview and laboratory guide. In this study, we focus on attentive listening. What is attentive listening? In attentive listening, the user does most of the talking, so this is user initiative dialogue. The listener utters listener responses, such as back channels. This kind of dialogue is needed in elderly care where people often desire social contact. I'll show you an example of attentive listening. When the user says, "Yesterday I went to a restaurant with my family," then the listener asks a question, which restaurant, to elaborate the talk. Then the user says, "The French one nearby the station, it was really delicious." The listener says, "That's nice." Then the user continues to talk. As you can see here, in attentive listening, it's important to encourage the user's talk. In this study, we aim to realize the attentive listening system using the Android Hierarchical. In the previous SIGDIAL conference, we proposed a preliminary attentive listening system. The key point of our system is to generate various listener responses. The purpose of this study is to realize a fully autonomous Android attentive listener for the Android Hierarchical. In this presentation, we report a dialogue experiment with elderly people. The main purpose of this experiment is that we compare our autonomous system with a voice system controlled by a human operator. Then we will find the gap between the system and real human. At first, I'll explain our attentive listening system. This is the list of listener responses. We use prosodic information of pitch and power and automatic speech recognition result as input. Then we try to generate these responses. I'll explain them one by one. We generate back channels that are short utterances such as yeah in English and in Japanese language. We made a continuous prediction model based on prosodic features. So it can generate back channels anytime, even when the user is speaking. The system also generates generic responses such as I see or I got it. If the input user utterance is short, this would be just yes. Since these responses can be used in any input dialog context, these responses work as kind of backup responses. For the next responses, we detect a focused word of the user utterance. Here, we use a simple heuristic rule that the focused word is the latest noun or adjective. For example, if the user says, I went to Paris to visit a museum, then the focused word is a museum. Using this focused word, the system repeats the focused word. For example, in the previous example, the system says a museum. The system also generates elaborating questions using the focus word. We concatenate the focus word with interrogatives such as which, when, and what. For example, in the previous example, the system asks a question, which museum? Generating these focus word-based responses, we expect that the system shows understanding of the talk. The system also does the sentiment analysis of the user utterance. We use a sentiment word dictionary to recognize the sentiment as positive, negative, or neutral. If the user utterance is positive, then the system generates that's good or that's nice. If it's negative, the system generates that's bad or that's hard. We also use another sentiment dictionary which has the wider coverage. Analyzing the sentiment with this dictionary, we change only the prosodic pattern of generic responses. Using these responses, we expect that the system shows empathy for the user's emotion. We generate several responses using these generation modules. But finally, the system has to select the proper one among them. As you can see here, we designed the priority order according to their difficulties of generation. Assessments are the first priority, followed by elaborating questions, repeats, generic sentimental responses, and generic responses. We implemented this attentive listening system for the Android Hierarchical. Then we conducted a dialogue experiment. The subjects were 20 Japanese elderly people. We asked them to prepare 2 topics: most memorable travel experience and delicious food you recently ate. The dialogue time was set at 7 minutes. We used our original speech recognition model, and the word error rate in this experiment was 33.8%. In this experiment, we compared our autonomous system with a WOS system. We asked a human operator to use the same set of listener responses as our system, and to select the proper one by herself. We also directly played the operator's voice through the speaker of Ergo. Each subject talked with and evaluated both of the autonomous and WOS systems. So this is within subject comparison. I'll show you a video from this experiment. This is the WOS system.
子供も大人もみんな好きやから、たくさん食べて、それがすごい楽しみなんです。素敵ですね。はい。ちらし寿司もあるんですけどね。
This is the autonomous system.
アメリカのニューヨーク行った時も、食事の値段がすごく安いんです。
どんな食事ですか？
朝はコーヒーとアップルデニッシュ、今よう思い出したわ。
Here, I report the 2 kinds of evaluations. The first one is a manual evaluation of autonomous system. We manually evaluated each system utterance by ourselves. Here, we made 3 metrics. I report one by one. The first metric is no error. This metric measures, is it linguistically correct? Concretely, we checked, was the repeated focus word actually uttered by the subject? As a result, most of the system utterances were no error. The second metric is reaction. We checked, did the subject show a positive reaction after the system utterance, such as, oh yes. As a result, more than 80% of the system utterances elicited the positive reactions of the user. The third metric is appropriate. We checked, is it appropriate as an effective listener response? So this metric is the most strict one. As a result, about 60% of the system utterances were acknowledged as effective listener responses. The next evaluation is subjective evaluation on each system. We compare the autonomous and WOZ systems by this evaluation. We used 19 question items in 7-point scale. Here, we show only 5 questions, so please check our paper for the result of all the questions. At first, even in the autonomous system, the evaluation scores were over than 5 in the 7-point scale, which is good result. When we compare the autonomous system and the WOZ system, on question 11 and question 12, there was no significant differences. Question 11 is the robot listen to the talk with focus. Question 12 is the robot listen to the talk actively. These questions are about the basic attentive listening skills. On the other hand, on questions 13, 14, and 15, we observed the significant differences between the autonomous system and the WOZ system. These questions about understanding of the talk, showing interest and empathy. These are more sophisticated attentive listening skills and require deeper understanding. So we can say that our system achieves basic attentive listening skills, but as we can see here, there is a gap between human and system for more sophisticated skills. This is left for future work. This is summary of this talk. In this presentation, we explained our attentive listening system for autonomous Android Ergo. And we also reported the dialogue experiment with 20 elderly people. Thanks for watching this video. Thanks for watching this video.
I've closed YouTube. Hello, hello.
Hey, hello.
Hi, are you Koji?
Yeah, I'm Koji. Yeah.
Nice to meet you, Koji. I'm Matthew Marge. I don't know if we met before, but you're where are you located? What university or institution?
I'm from Kyoto University, Japan.
Kyoto University. Okay,
yeah.
Of course. Yeah. Nice to meet you, Koji. I'm Matthew Marge. I don't know if we met before, but you're where are you located? Oh. What university or institution? I'm from Kyoto University. Japan. Kyoto University. Yeah, of course.
I hear. Wait, I muted.
There's an echo. I'm not sure if we're recording or not.
We are live. That's my bad. Sorry.
No problem.
Can
are we
I?
still
I'm
live?
gonna
Are we live now? We're going to be live for the.
We're going to be live. This is the same
Sounds good.
Zoom session that was doing the pre-recorded videos. I'm going to share my screen really quick again.
Sure.
So here we are in the middle of RoboDial 2.0. We just heard presentations for 4 papers and the introduction by Oise. That's so. There's a slight schedule change that we changed at the last minute here. We're going to go ahead and do the QA for the 4 papers that we just heard about right now, and that is right here. So if you scroll down, there's live QA session for special session papers, 45 minutes. You can click on that and join the live QA. And those of you who are waiting, I will let you in. And then following that, we will have the 2 demo papers, and that will proceed the same way as it proceeded before with the demos, where we will have 3 different things you can be doing. There will be a live interactive meeting for the 2 demo papers, and those are both linked right here. You can join those. One is a Google Meet, and the other one is a Zoom meeting. And you don't need to have anything special installed for Google Meet. And then simultaneously on this live stream that we're looking at right now, you will see this. You will see the pre-recorded videos for the 2 demo papers. That's, I think, it for me. We're a little bit early. We have a few minutes, so we can let people join.
Sounds good.
And like, kind of stop sharing here. Stop sharing. There we go. Okay. All right. Now, Matt, it's all yours now.
Okay, great. Well, thanks, Casey. For those that you may not know me, I'm Matthew Marge. I'm a research scientist at the Army Research Lab. And I'm the session chair for this live Q&A. So first, welcome. This is the 2nd RoboDial event we've had. We had one in 2018. I first want to thank the authors for contributing to a really great program. It's quite varied in the type of research being done on human-robot dialogue in this work. And while I was certainly hoping this was going to be in Boise, and we would have actually brought some robots too, I'm really glad to have the opportunity to talk virtually, and hopefully that we can reach out to more folks than we would if we were all in person. So my proposal for going forward with the session is to go through all the papers 1 round first. And so maybe 5 to 10 minutes per paper, and then we'll come back to any other questions for each paper after we go through each one. So I will also mention that you're welcome to either contribute directly by speaking in this chat or the channel we have here, or you can post a question to a card on Trello. You have specific questions there. And beyond that, within the Zoom meeting that is streaming, I'd like to ask anyone who wants to ask a question to raise their hand virtually, and then I'll call on you. And just a friendly reminder to close the YouTube live stream if you're going to join the Zoom Q&A. And I welcome anyone who is thinking about asking a question to join the Zoom Q&A. I'm hoping it to be a very fruitful discussion. And anyone that thinks they might have a question, we should have plenty of time. We have about 45 minutes for our Q&A. And I'm happy to see some familiar faces already in the Zoom chat, and hope to see some more very soon. But before that, I think the streams have completed. All the videos have been presented. Just want to check everyone is in the channels that we're representing papers. So I have Felix here for the first paper. Is that right?
Yeah, I'm here. Great.
And then David or Casey for the second paper. Is David joining us, Casey?
David won't be joining us, so I'm gonna.
Okay, Casey, you'll field
today.
it. And then, do we have someone from the Learning and Reasoning paper? Keting, Shiki, Peter, or Xiaoping? Let's wait. There may not be someone in for that question, that paper yet. And we also have Koji here for the Erica paper.
Yeah, and also the Divesh is here.
I'm also here as well. Yeah.
Excellent, Divesh. Great to have you too. And you're here for which? You're here for the Erica paper as well. Yep. That's the second author. Okay, great. All right. Well, I think we're ready to get started. So we'll wait again for the third paper. Hopefully, someone will join us before their turn. Let me start with the It's About Time paper. Does anyone have questions about this paper? This is about turn taking. I see that Nikhil has a question.
Yeah.
All right, go ahead.
Yeah. So yeah, I really enjoyed that paper. I had a question about since you did basically simulation of speech input with text, I was wondering, because the speech recognition is noisy, could the robot interrupt and reply if the incoming speech appears to be nonsensical based on prior input? So often you might swallow your words while speaking. So if the person says, drop the apple on the table, but for some reason the speech recognition drops the on and the input comes through as drop the apple the table, could the robot pick that up and respond with, that doesn't make sense, or maybe even infer that there's a missing on there?
That's a good question. So right now, the predictions, it basically tries to generate predictions based on the training data set that it got. So if it's not able to generate a prediction, it's not going to come in. It's not going to come in and produce the interjacent overlap, which was, the failure explanation. Like, oh, sorry, I couldn't do that because blah blah blah. So the only time right now that it will actually do that is if it can't do the action that's associated with the prediction that it made.
Okay.
If it makes a nonsensical prediction or a prediction that it doesn't have. Well, let's say forget about the fact that there's no action there. If it just predicts something that's not, in its vocabulary, let's say, then it's just not going to do anything with that. Then it will treat that as a normal utterance. It'll wait for the full thing to come in and then do whatever it normally would have done with that. So it wouldn't produce any kind of early response for that, and it will probably produce something like, "I didn't understand what you said," or "Please repeat," at the end of the utterance there.
Okay. All right. Thank you.
Sure.
All right. Any other questions for Felix? See if anyone's hand's raised, or feel free to jump in.
I have a quick question.
Sure, Candy.
Yeah. Most of the examples that you gave involve really short utterances, and they're in a kind of very task-oriented, limited kind of do this kind of thing. Can you imagine what kinds of changes you might need, or whether you thought it would work just the same if you had much more complex interactions, still in the task-oriented world, but more complex than that?
Yeah, so that's clearly a direction for future work. We wanted to start just at first to go with very simple kind of directives, and we were able to find a corpus that had exactly that kind of data. But yeah, obviously real dialogue, outside of like a lab demo kind of setting is going to be a lot more complex than that. So you might see like indirect speech or different kinds of statements or questions as opposed to just a simple directive. So in that case, I think that the prediction model itself will have to be improved for that. So right now we're using a bigram language model trained on our corpus, which is a very simple approach. We used it because it's quick and we need to do this in real time. So it's an approach that works, and it also considers some of the cues that we were interested in, mainly the lexical and syntactic cues. So that's why we use the bigram model. But I think for dealing with more complex utterances, we would have to use a more involved, a more complex prediction model itself. So I guess that's the direction I would take to improve on this in the future.
And if you had a more complex model, do you think you'd still be able to do the very nice prediction capability you had for, okay, the sentence will end roughly here, and that seemed to work pretty well?
So yeah, so in that case, we may have to use other cues as well. So right now, like I just said, we use the lexicosyntactic cues. We know from human studies that people use all sorts of other cues, prosody being a big one now, even visual cues potentially, like eye gaze or gesture. So I suspect that we would have to use other cues as well, in addition to what we have. And our framework supports that as well. This is just kind of like a proof of concept showing a basic scenario in which it works. But I think it can definitely be expanded upon with additional cues.
Thank you, Candy. I have a question about the bigram model, which that's used for utterance prediction. So I was wondering if it can be improved by incorporating fill pauses or other speech artifacts. How would you imagine kind of incorporating those into the model?
So we actually looked at different kinds of disfluencies in the paper, but this was not in, it didn't make it into the talk just because of the limited time that I had. So we did consider utterances in which there was, different kinds of filled pauses, different kind of unfilled pauses in the input as well. And basically what we did was we just kind of filtered them out, but we took the timing of them into account. So we assumed that they had a certain kind of like fixed timing associated with them. And the prediction, when we estimated the utterance duration, we would take that timing into account. And the results for that, it's in the paper, but basically we found that predictions that were, if the prediction was made after it already saw the filler in the input utterance, it would take that into account, obviously. But in cases where the filler was towards the very end, we had one subset where there was a 200 millisecond pause right before the final word. In those cases, the system, not surprisingly, would make a prediction before that even occurred, before it even saw that filler or that pause, and it wouldn't take that into account. So it was off by about 200 milliseconds in those cases. So yeah, we did explore a little bit about disfluency in the current work.
Excellent. Thank you, Felix. Any other questions for Felix in the group here? Okay, so that's a good, we'll come back to you, Felix, and go on for the next paper. So the next paper was David and Casey's paper, Learning Word Groundings from Humans, facilitated by Robot Emotional Displays. I just want to open the floor for any questions on this paper. We have one I know that we have from the card. Vikram posted one. He said, nice work. I was intrigued by the bimodal distribution of participant ratings at the end. Did you notice at what scenarios fell into each mode of the distribution? So he's curious whether there's a pattern there.
So can you hear me okay? I got an answer from, just making sure things are okay. Okay, I got an answer from the first author on the paper, David, who unfortunately can't join us, SIGDIAL, but he says, depending on what the user saw, or what they were, I guess, experiencing, they were more successful in teaching Cosmo more words. For example, they understood how to conduct the interaction better. When they just figured out how the interaction could work, they found Cosmo more intelligent and more engaging and more interesting, even though they may have been the ones who were doing most of the work, trying to make it more engaging. The fact that Cosmo is the way Cosmo is kind of motivates people to do that for some reason, which we found in some prior research, just by the way it looks and the way it sounds. They want to help it. They want to teach it. So, but that's not any different from like child development studies that show that when you're talking about how like adults interact with children and children are learning their language for the first time, it's very egocentric to the child, and the adult helps the child learn by basically doing stuff for the child. It's not often the case that the adult, at least when they're first learning words, the adult shows them an object and says, here's this object. So they're trying to get their attention. It's usually the child that already has their attention on an object, and the adult says, well, that's a bowl, or that's a ball, or a spoon, or something like that. So I don't know, Vikram, if that answers your question, but it really just, it'd be nice to dig into that data a little bit more and tease it apart.
Yep. Oh, just want to let you know, Casey, that Vikram's joined the channel, so he's welcome to add any clarifications or follow-ups.
Yeah. I guess not right now.
Oh yeah, that's fine. So any other questions for Casey?
It really just.
Oh. Yep. I just want to let you know, Casey. Applications and follow-ups.
Yeah.
Yeah. Thanks, Casey. That sounds that was good. I think we need to follow up more regarding some of that data. I think it'll, like you say, it could be interesting to analyze some of the reasons for these post hoc. But yeah, I think that answers my question.
Okay, I mean, I agree. Definitely need to spend more time on this, and we hope to beef this up a little bit more. I mean, I have a demo for our SDS stuff. We're going to put this into that and make it a lot more systematic. But we had 21 participants, and even though that got us some interesting results that we were able to tease apart, there's still a lot of, we could still definitely handle a lot more participants and put them through this, and that would give us a much better indication of what's going on.
Great, thanks.
Thanks for the question. Any other questions for Casey? I have a few questions certainly about that work. I thought it was really fascinating because it does leverage a really small platform robot. So I was wondering, so the emotions you evaluated right now were understanding and confusion. Mm-hmm. What emotions would you want to directly explore next?
So,
and which would correlate with the introduction of, let's say, language with a vector instead?
Right. So our 2019 paper that was in RSS looked at 16 emotions, and this was based on psychological research that said I mean, these aren't like the base emotions, but they're kind of, it was a nice spread of emotions because you have there are 16 emotions like joy and sadness and frustration and anger and those kinds of things, but then they're all kind of positive and negatively valenced. There's opposites within that set of 16. So there were 8 pairs of positive and negatively valenced things. And that's kind of the set we're working from. In that paper, we collected a lot of data that we didn't use it in this paper, but it helped steer us in the direction we wanted to go for this paper. Because Cosmo is, marketed as a robot for children, for it's a toy. So it has nearly 1,000 pre-scripted behaviors that someone can just invoke. And we did that with the Python stuff, with the Python SDK. And we recorded these nearly 1,000 behaviors and put them out on Mechanical Turk and asked people to rate them for one of these 16 emotions and also make descriptions of them. And the 16 emotions were able to predict the emotional state that the human would assign to the robot given some behavior that the robot performs. So we'd want to expand it to at least those 16 emotions and then build it out from there. We also have a SIGDIAL paper. That's kind of the next step after this. SIGDIAL's, I guess, happening later this month about grounding into those emotional states as they're represented from the emotion model. But this only considering 2 emotions to facilitate the language learning part where the robot didn't know anything, completely cold start, no words known, and emotion helped facilitate its learning. That was a good place to start. But like with Vikram's question, we need to do this with more participants, and we need to do this with more emotions. I think it would help out a lot. But then if you have these 16 emotions, if you really want to tease apart what's helping the language learning process, we would really need to get a lot of participants.
You mentioned 1,000 prescripted behaviors. Now, do any of those involve the motion of the robot? So how it could, perhaps the robot expresses its emotion through motion?
Well, you can read the RSS paper that we published in 2019 that kind of describes them, because a couple of things we found, and this isn't this paper, but I think it's part of the discussion at least. That paper, each of these emotions has an ID value, and it's a string, and you can look at the string as these words in it that the designers said, well, this is a show of anger, this is a show of happiness, or something like that. So we had at least those words in what the designers thought they were doing when they were designing the behaviors. But when we had the Mechanical Turkers rate them and label all of the behaviors, there wasn't a whole lot of agreement between what the designers thought they were putting into it and what the people perceived. Like someone might have thought, well, the designer might have said, well, here's an angry behavior, but someone might have said, oh, it looks like it's happy even. So it really depends on the context that it's showing in. Our data collection was very, I guess, context independent, or at least we were trying to be. But still, people will assign emotion to it. I don't know if that quite answers your question. They weren't tagged for emotion necessarily. We had to look at the way the designers named the different behaviors. They weren't necessarily to show emotion. That wasn't always their primary purpose, but in some cases, maybe about 300 or 400 of them, there was some sort of an emotional slant to it that they were trying to portray.
Well, yeah, I feel like certainly with the Cosmo, it can like gesture downward, and that might be some sort of sadness. So is that something you want to explore next?
Well,
kind of
this divergence into emotion wasn't something I was planning on doing in the first place. It was yeah, well, and we've spent quite a bit of time on it now. We've gotten 3 papers out of this the emotion side of Cosmo now. But it is case, I mean, this is the Yekaterina Novikova's work. She spent a lot of her entire dissertation is about how it doesn't matter what a robot does. When humans are put in front of robots, they're going to interpret any movement with some kind of an emotional display, even if the designers of the robots never meant any emotional display, like a Roomba. It's a vacuum. It looks like a hockey puck. But some people are like, well, it's trying to kill me. It kept following me, or it's trying to kill my cat or something like that. Clearly, these things don't have emotion. They're just displaying behaviors that people interpret emotionally. So no matter what you do, they do that. And that has to be taken into account when you start doing dialogue with robots, because if the robot is moving this way and looking up, at a certain point in your dialogue, right after you ask a question, you're going to interpret it. Maybe it's confused, or maybe it's thinking or processing or something like that. You have to take that into account when you're designing your robot and putting the dialogue system into it. So that's what happened to us as we were doing this. We realized that people were going to interpret whatever Cosmo did emotionally, and that sent us down this path.
Thank you, Casey. Ifra from Brown has a question.
Hello. It was a great talk, and this is actually a follow-up question to Matthew, and I think that maybe this was explained in the presentation as well. But right now, for emotional display, are you only using the screen display, or are you also using, for example, the motion of the wheels or something? And yeah, so it's the same. That what do you plan to do in the future as well?
We're using 3 features, well, 3 modalities, I guess. One is the motion represented as the internal robot state. So there's a vector that represents everything that's happening to the robot at any given time. Like if its lift is in its lift position, its head position, its roller position, all that stuff. So, and that changes at each state update. So we could get 1,000 of those every 2 or 3 seconds. That's how we represent motion. But we also gather the information about, well, I mean, the humans are looking at it. So they're the ones making the interpretation of what its emotional state is. So if it makes a sound, they're using that. If it moves, they're using that. The screen is actually very important. But this goes back to our RSS paper. Our RSS paper showed that different modalities lent themselves to different emotional interpretations. For example, confusion came through the face a lot. But frustration, or no, surprise was one of the emotions, and it was through movement. The movement modality was really important for surprise, because when the robot was surprised, it would lift its lift up and roll backwards very quickly. And it wasn't, I mean, it could show something in the face like widening its eyes or something like that, but that didn't seem to be as important as the movement. So those were the 3 modalities we used in that paper. And those were used in this paper as well. We weren't trying to model anything or predict anything from them. Like they weren't part of our grounded classifier for the dialogue task, or learning words or anything like that. It was strictly to the visual objects. But we, in the future, we are going to use those. In fact, I referenced Yekaterina Novikova. She has this really nice paper where, because if you're thinking about any robot platform and you want to do something with it, like represent its states so you can model it for its emotion. She has this really nice set of features that you can map any robot to. It's about 24 of them. And it's a nice dynamic representation of how the robot state changes over time. And we've sort of switched to those to see if they're useful, and we've found some much better results. Like we've gotten better results from compared to our RSS paper last year. Just using the internal states have nothing to do with the face. Information has nothing to do with the audio that the robot is producing. So that's one direction we're going down, and I think it's a worthwhile direction. But I don't want to abandon what the face is doing, because clearly that's very important, especially as expressive as Cosmo can be with its OLED face. But also the audio. We don't do much with the audio. I mean, it has a speech synthesizer, it has a cute little voice, but the pre-scripted animations that the designers have put in audio artifacts that aren't words, it'll do stuff like whoa or ah, or, stuff like this. And we can't really do that. So audio isn't quite as important. We're not focusing on that as much as we are on the movements of the robot represented by internal states and the facial features.
Great, thank you.
Yeah.
Thank you for the questions. Yeah, let's switch now to the third paper in our session. And Shiki is here to answer questions, I believe.
Hi.
Hi, Shiki.
Hi.
Welcome. So Shiki's got the paper Learning and Reasoning for Robot Dialogue and Navigation Tasks. And I want to first ask, does anyone have any questions for Shiki?
Actually, I was thinking that I'm here to support the first author, but not sure why the first author is not showing up. But yeah, I'm ready to take questions, if any.
Sure. Well, it's certainly what's interesting is it's very interdisciplinary, right? This is really fundamentally a robotics and dialogue and, as a sort of merged sort of research. We have a question from Ifra.
Hello. So in your slides, when you were presenting, you had one place where you were comparing the KRR and the model-based reinforcement learning combination policy with the static policy. So I just wanted to confirm what the static policy over there meant. Was it pure KRR or was it pure like RL? So yeah.
I'm not sure I get your question. So we have two components. One is the knowledge representation and reasoning was built on human knowledge. And the other one is model-based reinforcement learning that is interacting with the environment to gain the dynamics and the reward function. So sorry, could you repeat your question?
Yeah, so in your paper, in the experiment section, you're comparing the policy that is learned by, I'm not sure if I can share my screen or something, but where you're talking about like learning to dialogue and navigate from navigation tasks, there you're comparing the KRR RL policy with the static policy. So I just wanted to be sure what that static, which is your baseline. So I just wanted to make sure what your baseline is.
If I remembered right, the baseline method is not, so the connection between the knowledge representation and reasoning and reinforcement learning is disconnected. So the robot can still navigate in indoor environment to figure out, oh, this is a busy area, or this is under strong sunlight and it's dangerous to navigate through this area. The robot can still figure out that, but this information cannot be propagated back to the knowledge representation and reasoning module, which means when the robot is learning from navigation, such information cannot be used in other tasks. And in this domain, it's a dialogue task. So the high-level idea of this work from the dialogue perspective is that the robot communicates with people using natural language, and they talk about how to complete navigation tasks. So the human may say, robot deliver something from this room to the other, and the robot just using unreliable speech recognition to figure out the task and do it. So that's a dialogue part. But the thing is that the navigation tasks can be of very different difficulties. So sometimes the humans say, navigate from this end of the corridor all the way to the other end. It may take a lot of effort. And sometimes this is very easy navigation task. So we want to let a robot, when the robot is free, to just navigate around and figure out which part is difficult, which part is easy. And then when the robot and humans start talk to each other, they know that, oh, it seems like the human wants me to navigate for a long distance through a dangerous area, then I should be very careful. If this is not the task, I shouldn't really, I mean, making a mistake on such dangerous tasks can be very significant, can produce significant consequences. So there's a connection between the two. And when the baseline is that the robot can still complete navigation tasks, dialogue tasks, but the difficulty of these navigation tasks cannot be added back to the dialogue system. So it's not aware of these navigation tasks are easy, these are the challenges. So it basically doesn't make a difference to make mistakes on different service requests. Yeah. Does that answer your question?
Yes, thank you. I had one more follow-up question, but I want others to actually, if others want to ask, they can go first and then I can ask. So
we have about 10 minutes per paper, so we have 5 more minutes left to talk about Shiki's paper. You're welcome to add another question, Nika.
Okay, so the fact that, for example, you said, and in the presentation as well, you were talking about, for example, in cases where the robot is not clear, it's going to ask questions and everything, and that's like the dialogue component. So over there, do you have like a set of prompts? Like there are different levels of clarification questions that you can ask at different granularity. So do you have like a fixed set of prompts at a certain granularity, or do you have it at different granularity? And if not, do you think that you're going to explore that in the future? And if that's fair.
So the dialogue management component is pretty standard slot filling, but we didn't do it using like Q-learning or deep neural network. Instead, we use model-based POM-DP methods. So basically, we provide all the dynamics and all the language actions beforehand. And the robot just need to figure out, okay, given that this is a bonus if I can succeed on it, this is a penalty if I fail in these actions, and then the robot should decide what action I should take. So there's no, it's modeled as a probabilistic planning problem instead of a learning problem. But in the sense of the state space, it's very typical slot filling. So if I remember it right, we have room, we have atom, we have person. So the robot need to figure out where this item, what item should be delivered where for whom. So that's a 3-slot task. Yeah. Yeah. Thanks for the question.
No, this is really helpful and clarification. Thank you.
Thanks.
Great. Any other questions for Shiki before we switch to the next paper? Okay, I don't see anyone here, but I do have one more question. It's really fundamental, Shiki, which is in your KRR-RL model, how did you structure your world model so that it could track probabilities? So your student, who the first author, Ketting, mentioned time and weather. I was just wondering what other factors would you want to include and how difficult would that be to do?
So yeah, that's a great question. That's actually a very fundamental question. So I have a AIJ paper, Artificial Intelligence Journal paper. It's in the second round review. Hopefully it's getting accepted. So I spent 30 pages just talking about, a few topics, including this one. Basically, we separate the domain factors into endogenous factors and exogenous factors. And exogenous factors includes, say, time and weather. So fundamentally, we want to include as many factors as possible into our dialogue system. But either we use PaLM DPs or we use reinforcement learning, deep reinforcement learning. Soon we find the scalability issues. So there's a fundamental trade-off about model completeness and computational tractability. And that's a big topic. In the journal paper, I listed a few factors we should consider and a few ways to tackle this fundamental challenge. But in general, I think that will take quite long to discuss about it. But this is a very important point. Yeah.
Right, great. Well, I think that's a great answer because it is a big question.
Yep.
Thanks, Shiki. So let's switch to the final paper in the session, a really fascinating paper about Erica, an attentive listening system with Android Erica, comparison of autonomous and Oise interactions. So we have Koji and we have Divesh and Kenta to answer questions. So let me first open the floor for any questions for them.
Hi, can you hear me?
Yes, we can hear you.
Hi, really nice paper. So I have a question like, so you use like both for the evaluation, the Wizard of Oise and the autonomous system. So did the participants know like if they are like participating as for the autonomous system or they are like part of the Oise system? Because like in both cases, the Erica was present and they were like having like a facial expression. So that was my first question.
Okay, thanks for the question. And so first, each subject participate in both of the conditions. And so actually we didn't ask the people which they noticed the difference between them. But in the casual talking, some people noticed that, but some people didn't notice the difference. Yeah, and for example, in the case of the autonomous system, some people say that this was really like a human like system, and also in the case of the Oise system, people say that this is really sophisticated AI something. Yeah. So but
So we've actually done previous experiments with like a Oise system with the operator, and I think like like quite a few people who did not know actually that there's a hidden operator there. They assumed that it was all automated. So it's actually quite difficult to know precisely how much they thought it was actually a robot. But in the case of the experiment, though, we didn't tell them, of course, like there's someone hidden under here, or whether it was automated or not. So we didn't reveal any of that part during the experiment.
So my another question is for the manual evaluation part. So you evaluated the reaction. So I mean, for the reaction, did you just like take into account the utterance of the based on the utterance of the system? I mean, can you please clarify how you measured that, like the reaction?
Okay, so the reaction okay, thanks. So reaction means the user's reaction after the Erica's utterance. So for example, we gave a correct evaluation if the user says that, oh yes, or that's right, after Erica says something. Yeah, this is based on the actual user's utterance, not the Erica's utterance.
Okay.
Great. Do we have any other questions for the authors? Take a moment just to see if anyone's raised their hand. Well, in the meantime, I have a question for you. So this work, someone have a question?
Well, I do too.
Go
but
ahead.
Okay. It's more of it's kind of a discussion topic. I'm interested in what Koji thinks about this. It's not necessarily specifically about your paper. It's more about Erica as a robotic platform to implement things like dialogue systems on. I have 2 books sitting here that I'm yet to read, but they're basically making the case that if you're going to build a robot, and we found this in our research, if you're going to build a robot, don't make it look more capable than it is. But Erica Erica looks capable. Erica is as human looking as I've ever seen, and it's an absolute engineered marvel. But what we found, for example, with Cosmo is if it even looks a little bit like an adult, they're going to treat it like an adult. And we didn't want them to do that because we wanted a first language acquisition task. So the moment you make a robot that's substantially more adult looking, they're going to have really high expectations of it. I mean, the video you showed in your presentation was excellent. I see these, the elderly care, they're interacting with it very well. So there's clearly some good stuff happening there. But my experience with robots and people interacting with them is they treat them differently based on how they look. And so I want a robot to look, I guess, not as dumb as possible. I want its look to be aligned with its abilities and to kind of have them grow together. And there's some other researchers who've made the case for this. So Koji, what do you think?
Yeah, it's really important factor, and it's difficult to answer. But so the Erica has the very high affordance. She has a human-like appearance, so people often think she can answer anything. Yeah, but so sometimes we have some difficult questions from the user, and she can't answer them, and it's really difficult problem.
Yeah.
So this is the reason why we have a specific tasks, social tasks for Erica. So, and also we say every time in the experiment we told people, she can't answer anything. And so for example, in the case of attentive listening, in this case, we say to people, please do not ask any question to her, and we make the restriction on the dialogue. This is our current limitation.
Yeah, I mean that's kind of what I'd expect. The anthropomorphization is very strong, especially with a robot like Erica. But thanks for answering, Andrew.
Yeah, I'll just add something here. So kind of, I totally agree with you actually that the appearance of the robot has a massive effect on the expectations that people have about it. I think what we want to try and, like, for this actual project, what we're trying to do is kind of push that in a way. So, like, how far can you actually go with this? These kind of dialogue systems, where that the dialogue that Erica produces is actually acceptable and kind of congruent with the appearance. Another thing you mentioned that you said that you don't want to make Cosmo look like an adult because of the task that you have. So in Erica's case, we try and have tasks which are kind of more, I don't know, I wouldn't say sophisticated, but they're more adult-like. So we have, like, I think we've done job interviews, which obviously you want kind of an adult doing. We've done like attentive listening, which is kind of representative of counseling. And then we've done speed dating, which is like, kind of pretty up there, but this is actually an adult thing. So in that case, we try to pick kind of scenarios where, you would have an adult do these things. So we have an adult robot. And you do adult things with him. So in that way, we do try and kind of match the task to the parents as well. I think. Yep.
Any other questions about Erica? Well, I have one, which is that, so I'm thinking about the target goal use cases for Erica, right? So in addition to the target goal of getting elder participants to talk more, have you considered what kind of beneficial activities Erica may want to suggest? So, for example, encouraging the person to go outside or take their medicine, something like that.
Yeah, so I agree with that. Yeah, target and so we have a similar target with this application, but the problem is that the Erica it's really difficult to bring out Erica to anywhere. Yeah, so so at the moment we are thinking of implement this attentive listening system for example, in the smart speaker and some other small robot like Cosmo or something like that. But we've not yet how much difference of the effectiveness of the attentive listening compared between Erica and the other small robot or smart speaker. But that's our interesting. Yeah.
Great. I mean, I think it's really fascinating to get all the pieces working and then evaluate this in a real-time scenario. You have automation and wizard. So I had a question about the wizarding. So you had one professional wizard in a sense, right? An actress, if you will. So how much training did that wizard have, and how hard of a task do you believe it was for the wizard? You know, what are they exactly controlling? Are they just doing typing of dialogue, or are they controlling the motions of the robot? Those kind of questions.
Okay. So actually they practiced only 1 hour before the experiment, and what they controlled was at first she controlled Erica's gesture, like a nodding and the eye gaze direction, which is quite simple. And also so in this case we directly played the operator's voice through the Erica's speaker. So I mean they didn't type. They just say something to the microphone, and we just play it. This is like a telephone conversation. Yeah.
But the lips were synced, so they
Yes.
synchronized mouth movements to the speech.
Yes.
So yeah, it appears she's saying it.
Oh, that makes sense. Yep. Well, I can tell you. Yeah, go ahead.
Yeah. Also, for some of the WOS things, there's some restriction on what they could say, so it wasn't totally free conversation. Like we had some set format of answers that they used as a guide. So we wanted to kind of replicate the automated system, the restrictions of the automated system with the WOS, which I think was a pretty novel way of doing it as well. So,
well, do you think the WOS data could be useful for training the automated system?
Yeah, I'm working on that, and
learn a lot maybe from the human operator. Maybe you want to have other operators or try other tasks.
Yes.
Yeah. So initially we did have actually free conversation with the attentive listening system, and based on that data, we kind of made some, like patterns of dialogue that we could use in the automated system. So at the way we chose, like we have different categories of responses. They're kind of based on what the real WOS operator said. But this was in previous experiments, obviously. So yeah, we try and kind of match that. But yeah, there's some things that are very hard for us to kind of patternize, like as well.
Great, thanks. So I have a broader question I want to bring to the table for everyone that was an author associated with this session. We only have a few minutes left, but I just want to ask if anyone has any thoughts on evaluation, right? This is a big problem in terms of evaluating human-robot dialogue. So does anyone have any comments on what they've learned from their research and what they would want to do in their next evaluation?
I'll say something really quick, I guess. You're putting people in front of these and they're interacting with them. So the evaluation does have to be human-centered, and that's always difficult. That's not surprising to the dialogue systems community. It naturally kind of extends when we look at robots, because you do have to put humans in front of these systems and test them out. The question is, what do you ask them and what do you have them do, and those kinds of things. We've used the Godspeed questionnaire and added our own questions to it, and that's great, but there's still a lot left to be desired. So I'll leave it at that.
I'll say it's kind of unpredictable. It's really, like we had people do the experiment where we thought, this is a rubbish interaction. Like the person's not saying anything. They're just kind of, doing generic responses. And then when you do the evaluation, they think it's really good. Like the robot's really great. And whether that has to do with the novelty of sitting and interacting with a robot, I think there's a lot of that going on there. So even if, I agree that you need human-centered evaluation, but there's like a lot of factors there that, I'm not really sure how we can kind of disentangle that from the, from the actual objective quality of the interaction itself. For me, that's a big one. Like, there's things that we think are not good and that the subject actually really enjoys. And I don't know how you can control that actually in terms of evaluation. That's for me, that's the biggest kind of obstacle there.
Any other comments for now on that evaluation topic? Either Felix or Shiki want to chime in for any comments?
I guess it reminds me, sorry, Felix, do you want to start?
No, go ahead.
Yeah, so it reminds me actually quite a few things. Like once I was using a mobile robot to do guidance tasks, and then we give survey papers and ask people, what do you think about our dialogue system? But people actually mention, oh, your robot is too slow. I asked the robot to guide me somewhere, but it's so slow. I feel the dialogue part is fine, but it's not very useful. We don't really know how to address such comments. It's part of the dialogue. I mean, we use dialogue to figure out the task, but it's actually beyond dialogue. So once it's with the robot, we need to consider the size of the robot, where this dialogue happens, the contextual information. There are so many things. And we do have some good simulators, but I think they're far from being realistic. So that's probably something we can look into and develop some better benchmarks for evaluation.
Yep. Great. And Felix, you have a quick comment?
Yeah, I was just going to say that in my paper, we didn't do a human subjects evaluation because we're still at in a previous step where we're trying to test the algorithm and the system first to make sure it works. But the next step would be to evaluate, kind of a user study with humans and see how they respond to this kind of behavior by the robot, and specifically in the cases when the robot overlaps the human, coming in early to explain why it can't do some action, for example. I can imagine situations in which that could be perceived as rude or, as like a form of interruption. But then again, there might be other cases, if it's a very fast-paced task and, they don't have a lot of time and there's a lot of back and forth exchange, maybe in those kind of cases, such kind of overlap would be desirable. So there's a lot of room to explore those kind of problems.
Great. I think I agree completely. Well, we have to wrap up. It is clear that from all the questions we were able to manage, there's a lot of passion and interest in this topic. So I look forward to next year's submissions. And I'm noting that we'll also probably see them at HRI or ACL or other conferences too. So thanks to all the speakers.
Thank you.
And thank you, Matt, for running this session. I'm going to share my screen really quick. The next part of this will be, oops, those are backwards. The next part of this will be the demo session. Sorry, the demo session. There's 2 demos for the RoboDial 2.0. We will play these on the live stream, but do please click on the live interactive meetings for special session demo papers. Click on that, and there's 2 meetings you can join. So you can ask questions to the authors. So there's 3 things you can be doing. One is watching the live stream of the videos, pre-recorded videos, and the other 2 are joining these meetings. So we're going to do that for the next part, and then we'll move into the late-breaking reports and position papers. I'll ask everyone to leave this meeting.
Hi, my name is Georgi Platonov, and I will be presenting our work on the system capable of answering spatial questions in a physical blocks world. The setup that we're using is depicted in this picture. As you can see, we're using several blocks marked with various corporate logos for unique identification. These blocks are also color-coded using the colored strips running along the block's edges as red, green, or blue. we use two Kinect sensors to track the block positions on the table, as well as various additional I/O equipment for audio-visual communication. The interaction is speech-based. We employ Google Cloud Speech-to-Text API, as well as animated child avatar, David, for communicating with the user. The following video fragment demonstrates the interaction with the system. David.
Hello again.
Which blocks are to the left of the Twitter block?
The target block and the Starbucks block are to the left of the Twitter block.
What is the leftmost block?
Only the target block.
What is the leftmost block?
Only the Starbucks block.
This slide shows the principal components of the system. The block's world tracker reads the data from the Kinect sensors and models the configuration of the physical blocks in Blender. This model serves as a sort of a mental image of the real physical situation that our system uses to make spatial judgments on. The dialog manager, ETA, takes in the user transcript obtained from the automatic speech recognition system and puts it through a specialized custom-built semantic parser that produces a logical form representation of the user's question. A specialized spatial component incorporates constraint solver and implementation of the spatial relations. Finally, when the answer for the question has been produced by the constraint solver and returned back to the dialog manager, it generates the reply, which is sent to the avatar app to be communicated back to the user. ETA is a dialog manager designed to follow a modifiable dialog schema specified using a flexible and expressive schema language. The main contents of a dialog schema are logical formulas with open variables describing successive steps expected in the course of the interaction, typically speech acts by the system or the user. These are either realized directly as actions or expanded into subschemas for further processing as the interaction proceeds. A key mechanism used in the course of instantiating schema steps, including interpretation of user inputs, is the hierarchical pattern transduction mechanism. Transduction hierarchies specify patterns at their nodes with branches from a node providing alternative continuations as a hierarchical match proceeds. Terminal nodes provide result templates or specify a subschema, a subordinate transduction tree, or some other result. ETA also incorporates the semantic parser that converts the transcripts of the user utterances into the unscoped logical form representation. The ULF is a general-purpose semantic parsing representation that is built on a formal, type-consistent model-theoretic foundation close to the surface form of English. It also preserves majority of linguistic phenomena such as tense, aspect, plurality, and so on, using various explicitly defined operators. You can see the example of a ULF for the corresponding English sentence below in this slide, and you can also see some of the mentioned type operators, such as, for example, plurality and tense operator. The ULF representation of the user's utterance is then further parsed into a data structure that we call query frame. A query frame is a hierarchical data structure that is depicted here in this slide that you can see. It consists of various predetermined slots that are occupied by various constraints and modifiers extracted from the ULF representation of the question. These modifiers and constraints include types, determiners, colors, numbers, as well as various intensifiers such as directly, slightly, and so on. This query frame is then augmented with additional information about the type of the question, for example, whether the question is asking for a specific block or a number of blocks that satisfy a certain property or a block color, etc. And then it is passed to the constraint solver for further processing. The query frame is then passed into the constraint solver module, whose purpose is to find the object that satisfies the constraints contained in the question. Constraint solver works by recursively resolving the predicate and the arguments contained in the query frame. By resolving the predicate, we simply mean mapping the preposition into the function that implements it. And resolving the arguments means finding all the objects that satisfy the argument constraints, such as color, number, type, and so on. Once all the candidate arguments are found, all the possible combinations of these arguments are formed, and the predicate function responsible for that relation is applied to every such combination. The output of the constraint solver is the set of tuples of this form, where the first component is the specific argument combination, and the second component is the confidence level, that is, the value of the predicate evaluated on this specific combination of arguments. Let's consider the following example question with the block configuration displayed on the right. Resolving the argument positions yields the following results. So the first argument, red blocks, is getting resolved to Twitter block and Mercedes block. As you can see from the picture, only Twitter and Mercedes block are red. And the second argument, arg1, is uniquely identified in the question itself, and so the system just returns the corresponding block. Applying the prepositional predicate above to every possible combination of the arguments yields the following values for each specific configuration. From these values, the initial answer set is formed, that you can see below. Finally, the highest value is being filtered out. This exact filtering process depends on the precise wording of the question and the values returned for each configuration of arguments. We model spatial prepositions as probabilistic predicates constructed from sets of factors, which are primitive geometric and functional relations that are usually accompanying or correlate with a specific spatial configuration. These predicates operate on the 3D imagistic scene reconstructed in Blender. Examples of factors are the scale distance between the centers of two objects, whether two objects are in contact, whether they are of certain shapes or types, and so on. These factors then are either linearly combined or maybe the maximum out of them is taken depending on a specific relation. For example, when one object is on another object, it is often higher than that second object and typically supported by it. So these two factors, relative height and support, are contributing to the computation of the relation of on. Not all factors potentially influence a relation are relevant in a given situation, so we check various combinations of them that correspond to different usage patterns or stereotypical use cases. In order to evaluate our system, we instructed several volunteers to ask spatial questions of the general type supported by the system, but without restriction on specific wording. They were requested to mark the system's answer as correct, partially correct, or incorrect. The proportion of correct and partially correct answers is about 80%, which, given the vague and subjective nature of spatial judgments, we find quite satisfactory. We also separately tested the performance of the ULF parser, and you can see the numbers on this slide. I should briefly mention that apart from answering the questions in a static context, we are also adding the capability of answering questions about past states and actions, such as block moves. This both allows for a more meaningful and realistic application of spatial relations and gives the interaction a more dynamic, dialogue-like flavor. And that's it. Thank you for your attention.
All right, this demo paper is RRSDS, towards a robot-ready spoken dialogue system. I am Casey Kennington. Along with Daniela, Lucas, Jake, and David, we worked on this dialogue system that we are demoing today. And we're all part of the computer science department at Boise State University. First, I want to talk about the requirements. Research in spoken dialogue system has advanced considerably in the last decade, but it's not enough just to put any spoken dialogue system onto a robot and expect everything to work. And these are the following requirements that make it harder. One is it needs to be modular. End-to-end dialogue is great, but SDS modules need to connect to and be informed by robot modules. It also needs to be incremental, and that processing needs to happen very quickly, as much as possible, as early as possible. Can't wait for verbal ping pong. It needs to be very fast. 3 is multimodal, input from more than speech. Sensors, robot cameras, all kinds of things need to come into the system to so it can make decisions about what to do next. Distributive means all these modules often individually take a lot of processing power. So we sometimes need to put different modules on different machines, like speech recognition or language understanding or something. And each of them might require their own GPU. So we need to be able to distribute this processing load and make it work very quickly and easily. It also needs to be time aligned, in that time delays and sensors and modules are accounted for. Like speech recognition might have a 500 millisecond delay, gesture recognition might have a 50 millisecond delay, but knowing what happened at the same time is really important. So those need to be aligned. And it doesn't hurt that it's in Python. Not a requirement, obviously, for SDS with robots, but given the way things are right now, Python is preferred over other languages. For this demo, we're going to try to approach 1, 2, 3, and 4, modular, incremental, multimodal, and distributive. And what we mean by modular is it's not end-to-end. Here's a typical dialogue system. Speech recognition recognizes audio from the microphone, gives you an utterance in terms of transcription. Language understanding gives you some semantic abstraction. Dialogue manager makes a decision and says something. That's your typical dialogue system. You can, of course, jointly model NLU and dialogue management with dialogue state tracking or belief state tracking. But if you want to make this incremental, it makes it much more complicated. Instead of working at the utterance level, waiting for endpointing, it actually is recognizing speech recognition word by word. So the NLU is updating its understanding as fast as possible. And there's ways to deal with this. There's frameworks out there. I'm not going to belabor those. The one we're using is the incremental unit framework introduced by David Schlangen and Gabriel Scanze. And then adding from modular to incremental is then multimodal. So instead of just speech in and speech out, or even just written text in and written text out, we need an object detection. We need lots of other sensors from a camera, from multiple cameras, from infrared, from bump sensors. And we need to be able to integrate those into the system. In this case, this example, we have speech recognition, which goes into an NLU, but then the NLU needs to know something about the world around it. If a robot is observing an object and someone says, get the red one, it needs to know what red means. It needs to know which objects are actually red. So we need a grounded NLU model. So I want to show you an example of our system in action before I tell you what's in it. This is the Misty robot. Misty, and this is this robot right next to me right now. Misty Robotics 2 puts out this robot. Misty Robotics puts out this robot. It's the Misty 2 robot since August 2019. It has some track wheels, arms, some nice sensors above its eyes here, and an OLED face. And all this demo is going to do is someone's going to say, please find something that's red. And then it looks around. So someone already said, find something red. It repeats red, red twice for some reason. And then it looks around a bit. It's feeding information from its camera right up above its eyes here into the dialogue system. And then it says that looks red. And the speech synthesizers on the robot is the thing that's making that utterance. The RRSDS that we have, these are the modules, and I'll go through them one by one. It's built on top of Redico, which is built on the IU framework. So if you're familiar with InproTK, which is written in Java, this is like that in a lot of ways, different in a lot of ways, but really nice, really easy to build on. I was very happy to see this come out last year. Thilo Michael is the one who maintains this, who wrote this originally, and he has a demo also at SIGDIAL, and I hope that you watch that. So we build everything on top of that. Everything that we have here is a module inside of Redico. We have a web camera. This built-in mic and Google ASR are underlined because they already came with Redico. We're leveraging them in our system. We also have a microphone array with 6 microphones on it. It does point of arrival and can filter out unwanted noise. It's really nice. We have some cloud-based stuff like Azure ASR, object detection, face emotion detection, mask RCNN for object detection also, which is local and written in Python. We have Keras object feature extractor using EfficientNet or VGG19 or Inception v3 or whatever you'd like. And then our NLU is a grounded language understanding component using the words as classifiers model. There's also incremental RASA for NLU. RASA, you're familiar with, is quite well used for chatbots and things, and it could be useful here for a robot. But anyway, we have an incremental version of it for our STS. OpenDial, written by Pierre Luzon, originally in Java, has been rewritten in Python, and we're using that as the dialogue manager. eSpeak is a speech synthesizer. We don't use it because we're using the onboard robot speech synthesizers, but it exists. And then we have the Cosmo modules, camera, internal states, action, and speech. Same thing with the Misty Robotics, Misty 2 robot. So this is the Cosmo robot, and this is the Misty robot. They have similar kind of look and feel, but though the Misty robot is much taller and its head can move around a lot more, Cosmo is very small, no taller than say a softball. For distributiveness, you can use 0MQ to send messages across different processes or different machines across the network. We can also use a robotic operating system. We tested that with the Turtle Sim, and we use the platform for situated intelligence for logging. This is all tracked with on a Trello board. If you're interested in contributing or want to learn more about these individual modules, send me an email. I'm the first author on the paper, and I'm happy to add you to this. The system that we actually are using on these two robots for our demo is the ReSpeaker, the array mic that goes to Google ASR. That gives us incremental word units on the output. And then the robot camera is looking at the scene, but then it's actually the Mascar CNN object detector will find a single object and just pick one, kind of not at random, but it'll pick the one that's the biggest one. And then it will move the robot to look at that kind of in the middle of the screen, and then it will use the Keras feature extractor. So it'll take the bounding box around that object and ignore everything else, grab that object, kind of isolate it from everything else in the scene, and then we apply that to the feature extractor. So we have this vector that represents this object, and then the WAC model, when we train it, it learns which features fit to certain words. So if someone said the word red in a referent expression and the object feature extractor had this vector representing an object, it can differentiate between red things and not red things. And it can do this for lots of words that it's been trained on. And it outputs an object match, says, okay, that's a good one or a bad one above a certain threshold. And then PyOpenDial has some decisions it makes. It decides, do I say that's a match? Do I turn and randomly find another object? Do I go towards an object to get a better look at it? So there aren't too many decisions that it's making. It's rule-based at this point, but OpenDial is nice. You can use training data, wizarded data, or offline data to train right now a dynamic Bayesian network or a deep learned model as a POM-DP. And of course, there's robot states and actions that are also modules in the bot. But this is our system. Everything logs to the platform for situated intelligence that we can then use for offline evaluation or an offline analysis. Here's the Cosmo robot. Very similar to Misty. Someone says, look for something that's yellow. So it finds an object and it explores it a little bit more. Then it says, not yellow, that looks orange. And then it makes a decision to kind of randomly turn in some other direction to look for another object. And then it sees this object and says, come on, out with it. That looks yellow. Okay. Future work, better integrations with Psi. So we want to be able to program everything in Python, but have Psi do the heavy lifting, and we're working on that because Psi fulfills the time alignment requirement. It's really nice time algebra, great for login, visualization tool, and playback. We also want to add more modules, including language generation. And to show you that this is out there for you, this is on GitHub. So there's a URL to this in the paper. So please help us out with this, and we hope that you find it useful.
Hello, I'm glad to introduce to you our multimodal corpus of human-human and human-robot conversations. It is the result of an interdisciplinary project hosted by and funded by Aix-Marseille University. Hello, I'm glad to introduce to you our multimodal corpus of human-human I'm glad to introduce to you our multimodal corpus of human-human and human-robot conversations. It is the result of an interdisciplinary project hosted by and funded by Aix-Marseille University with 3 different expertise. My field is social cognitive neuroscience. I investigate the neural basis of social interactions, but I also collaborate very closely with experts in natural language processing from the Department of Linguistics, as well as human-machine interactions from the Department of Computer Sciences. In this experiment, participants have a natural conversation with a human, me or a woman, and a robot. In order to have something to say, something to talk about, we built a cover story. Participants believe that they participate in a neuromarketing experiment in which they are shown images of a forthcoming advertising campaign, and they have discussing with another person to figure out what's the message of this forthcoming campaign. I will then show you a video that describes the experimental setup. In this experiment, participants are first installed in the scanner and equipped with an audio and video system to allow them to discuss live alternatively with a confederate of the experimenter or a conversational robot located outside of the scanner. I will now give you some more details about the experimental paradigm. So the person in the scanner is talking either with the confederate of the experimenter or with the conversational robot. They see an image for 10 seconds and then discuss during 1 minute with the human. They see another image from the same campaign and then discuss another minute with the other robot. This is repeated 12 times for the human and 12 times for the robot for each participant, yielding 24 minutes of conversation for participants and a total of 600 minutes of conversations. Here is an example of a 1-minute conversation with the human. At the beginning, you will hear the scanner noise, then it is denoised post hoc. So here's a 1-minute conversation with the human.
Un masque de Batman? Ouais, bah avec les yeux et la bouche et... C'est ça, ouais. Donc... Alors là, c'est vrai que ça laisse un peu dans le flou, mais... Ouais, mais c'est déjà lié à l'alimentation, je crois. C'est quelque chose qui a à voir avec le... Oui, ou alors avec les super-héros, on sait pas, avec Batman. Ou avec les super-héros, Batman.
And here's an example of the conversation with the robot.
Cette pomme a des grands yeux.
Elle a des grands yeux et elle est à l'envers aussi, donc est-ce que ça signifie quelque chose?
On dirait un Spider-Man, cette pomme.
Ouais, on dirait Spider-Man à l'envers, une pomme rouge.
We record a certain number of raw signals. The video that the participant is seeing of the human and the robot, and what the human and the robot is saying to the participant in the scanner. We also record what the participant is saying, as well as his eye movements to know what he's looking at, and of course, his brain responses, as well as other physiological data. These raw data can be combined to make higher level behavioral data. The next step is the transcription of the dialogue. This allows us to ask very simple questions already. So what is specific to speaking to a human in blue or to speaking to a robot in green? By using the transcriptions, having a look at the brain activity when the person is speaking versus when it is listening. In conclusion, we have the first fMRI corpus of a natural social interaction, a conversation with a human and a humanoid robot. This unique data set is used to address questions pertaining not only to human-robot interactions, but also to natural conversations and to social interactions. The future work on the corpus entails fine-grained analysis of the time series. But it's also important to mention this corpus is designed to be shared. Thank you for your interest.
My name is Nikhil Krishnaswamy, and I'm pleased to be presenting our paper, Situated Multimodal Control of a Mobile Robot, Navigation Through a Virtual Environment. I'm here on behalf of myself and my co-authors, Katie Krajewicz, Nate Dimmick, Peter Salas, and James Pustiowski from the Brandeis University Department of Computer Science. So a key change in recent HRI involves the development of new capabilities in communicating with and controlling robotic devices, including language interfaces and recently gesture. But what is still lacking is the ability to interact with the robot agent multimodally with integrated language and gesture in a dynamic communication. We've been developing a platform that we call Kirby that uses a number of existing technologies to facilitate this type of smooth communication using both language and gesture between a human and a robot. Kirby uses ROS, a custom communications bridge, Redis, our situated grounding platform VoxWorld, and the Unity game engine. We also use a Turtlebot 3 and Aruko fiducial markers to stand in for objects of interest in a simulated world. The ROS gazebo simulator contains the ground truth of our world. The robot sees the world using a LiDAR, and that information is then communicated to VoxWorld, which creates a 3D virtual rendering of what the robot perceives, and that's what the human interacts with directly.
Hello, I'm ready to go.
The human can see an omniscient view and a view of Kirby's perspective. The omniscient view can be manipulated, and the two views can be switched between. The human can instruct Kirby using just language. Turn left.
Okay, turning.
And a combination of language and gesture. Go here. In both cases, the robot in Gazebo responds to the directly grounded instructions.
Okay.
Certain modalities are better at communicating certain types of information. A precise location may be really difficult to describe using language, but using a combination of language such as the demonstrative here, along with the deictic gesture, you can communicate a precise location. This is a schematic of our architecture. On the right, you see ROS, where Kirby executes basic commands such as patrol, turn, go forward, information about the map, Kirby's speed, objects that Kirby encounters, and feedback that Kirby has to give to the user is communicated through the robotic services bridge and then stored as Redis keys, which are then picked up by VoxWorld, where the virtual Kirby is updated and where Kirby gives feedback to the user. Right here, you may have noticed me gesturing in a direction to make Kirby move in that direction, and that direction is in fact perspective dependent. Viewpoint is an important part of the interaction because it creates a shared epistemic space to enable common interpretation. Two-way communication in co-situated environments requires that the human be able to access all aspects of the robot's world, and the human has more background knowledge, as the robot does not understand what it sees, but can listen to the human. To that end, the omniscient viewpoint can itself be manipulated via gesture, so here I'm making a quote-unquote grab gesture to secure the camera, and then having it rotate in particular directions by gesturing in those directions. The line segments extracted from LiDAR data can be imprecise, particularly when Kirby is in the early stages of exploring the world, and they tend to shift a lot. We've been developing some machine learning techniques to ameliorate this. Here we see the data gathering process for the learning algorithm, where we load up a ground truth of the world and some previously gathered LiDAR data. We then match segments and execute transformations over them, such as align segments or close corners. The model is trained on this data, and the expectation is that in real time, it will execute those transformations over line segments that are extracted from LiDAR data as Kirby explores. We use a 4-layer feed-forward neural network to make these predictions. It's implemented natively in Unity and C#, and it causes Kirby to kind of hallucinate walls to provide a more interpretable visualization for the user, while the underlying line segment representation remains unchanged, which allows us to go from a visual simulation that looks like this, which is full of holes, to something a little more cohesive, more like this. Kirby is still very new, so we have yet to evaluate the system. We plan to give participants a target object in the environment defined that they then have to direct Kirby towards using the appropriate combination of language and gesture. VoxWorld provides a venue for a human and a robot to communicate within a shared epistemic space. So we imagine robots assisting humans in environments where humans cannot go safely, but they have to rely on the interpretive capability and background knowledge of humans to complete their tasks. Plenty of future work. Obviously, we need to support complex commands, and commands get more complex as the object domain gets more complex. We have the VoxML modeling language to model complex object semantics, and we need to be able to recognize those objects so that the robot can recognize a door and the human can point to that same area in the virtual world and tell the robot that it needs to go through that door. Kirby also supports learning novel gestures, so we need to link those novel gestures to the aforementioned complex commands. And here I'll actually make a shameless plug for my new position. If you're watching this on July 1st, the day of RoboDial, today I actually start as Assistant Professor of Computer Science at Colorado State University, where I'll be collaborating extensively with the large vision group there, which gives us a great opportunity to extend this collaboration of linking language to vision and gesture into the robotics domain further. So I want to thank everybody for watching this talk, and we look forward to your questions.
Hello everyone, my name is Ifra Idris. I'm a third-year PhD candidate in Human to Robots Lab at Brown University under Dr. Stephanie Delex. Today I'll be presenting a joint research work between Brown University and University of Hampshire with Dr. Momotaz Begum. My research is on grounding human-robot dialogue in environment sensors to help the elderlies in their activity of daily living. Activities of daily living include simple activities such as eating, getting up from bed, walking. And as simple as these activities might seem to us, they're not as simple for an elderly. An elderly needs supervision. An elderly, especially with dementia and cognitive impairment, actually needs someone who can help them in giving guidance for completing these activities of daily living. And this actually motivated us to ask the question that can we have a conversational robot that can act as a health pal and as a coach that can help the elderly in completing the activities of daily living safely. And therefore, in this work in progress paper, we actually are presenting a proof of concept implementation and a system architecture of a multimodal dialogue manager robots to assist the user by providing instructions for and monitoring the progress of cooking activity. Previously, work has been done in 3 domains, that is social robotics, virtual healthcare assistants, and conversational social robots, to help the elderlies set medical reminders or even act as exercise coaches. Added challenges for a task-oriented dialogue manager include the sequential nature of the task and further not just ensuring that the task is completed, but also ensuring the safety of the users. So to give you a better visualization of how a conversational robot might help an elderly in completing an activity such as cooking, we will show you a demonstration of an initial prototype that we developed. This prototype was deployed on Curry Robot. Hey Curry, I want to cook. Can you help me cooking?
Yes, sure. Which recipe do you want to cook?
Hey Curry, I want to cook hard-boiled eggs.
Great. Next step in cooking is heat the pot on high heat and bring the water to a full rolling boil. Do you want me to track to see if the activity is being completed safely, or will you tell me when you are done with this step?
Hey Curry, I will tell you when I am done with this step.
Yes, you can surely complete the activity on your own, but for your safety, let me monitor you and see when the activity gets completed.
Here you can see that for a step that is characterized by Curry as not being safe is monitored by the robot regardless of the preference of the user in order to ensure their safety. Hey Curry, you can surely monitor me.
Good job, you have completed the step safely.
So the first part of our system architecture is the standard dialogue flow model. That is, it does intent classification of the user message, gives this intent classification to the dialogue state manager, which then decides what should be the next system response. So this is the standard things. Nevertheless, our paper is actually focusing on actually giving grounded context for the interaction to the physical sensors by observing the environment. And further, we are also enabling a finite state machine architecture so that it can track the dialogue state. To give you more detail of how the context awareness logic is actually built, we actually look at the current user intent, combine it with the dialogue state to actually see that if the physical context actually needs to be invoked. And then when we decipher that, yes, the dialogue state needs to be invoked because we need to monitor the elderly, we actually exhaustively condition on the sensor values to see what is the appropriate system response. We also show a quantitative evaluation of our dialogue manager deployed on Curry. We show different system responses that are generated for all the combination of sensor values and show its distribution along with the distribution of errors over a total trial of 26. And still, we were able to achieve a success rate of 73%. There are still limitations to our initial study. For our extended work, we hope to incorporate real physical sensors instead of relying on the binary monitoring outcomes that we read off right now from a data file. We hope to make our extended dialogue manager generalizable enough over multiple tasks such that the response time is not compromised. Right now, we focused on synthetic data. We hope to curate a corpus of natural conversation with the elderly. And if you look at the error distribution, the errors were because of speech recognition, intent classification, and selection of action policy. We hope to experiment with different data-driven approaches such that these errors are reduced. So this paper, we actually show a proof of concept implementation and feasibility study of a task-oriented, context-aware dialogue manager, which is based on ADL activities to help the elderly in completing them, and we deploy our dialogue manager on CurryRobot. Thank you for watching our video.
Hi everyone, this is our position paper towards meaningful grounded conversations with intelligent agents, where we explore some of the limitations of current works and propose a way to overcome them. I'm sure you're all familiar with the proliferation of conversational agents around us, such as Siri, Alexa, Google Assistant, and many others, embodied or not, virtual or physical. For our purposes, we will not distinguish between virtual or physical agents, but we will categorize them as transactional and non-transactional agents. Our proposed model aims to shift away from the rigid slot-filling dialogues to a more realistic and flexible paradigm, and to handle concrete and abstract entities, as well as the evolving relations between them. Recent work on the field has mostly focused around machine learning approaches to conversation modeling, and in particular reinforcement and deep learning. While the concept is not new, lately there has been a trend to incorporate knowledge bases or knowledge graphs to better ground the conversation. In the paper, we discussed some representative works, but could not cover everything due to space constraints. It is undeniable that such methods have helped push the field forward over the last few decades. Despite this progress, however, there are still many limitations in current works. Most recent works model the dialogue as a slot-filling problem, or take a similarly simple approach. There is no distinction between soft and hard constraints, and while some works do handle dynamic knowledge graphs and unseen entities, no works can handle unseen relations, at least to our knowledge. Likewise, there is little distinction between the various types of entities, for example, objects which may be physical or conceptual, and the relations between them that may be dynamic. Many systems, particularly end-to-end trained systems, exhibit a lack of in-depth knowledge that users are quick to realize. A simple and repetitive language is also a general concern. Last, no system can really handle interactions over longer periods of time, primarily due to the lack of longitudinal data, where users talk to their assistant over, let's say, a year or two. Hopefully, this is about to change as we spend more and more time with our personal assistants. Aiming to address some of these challenges, we propose a middle ground approach between traditional pipeline systems and fully end-to-end trained systems by combining two existing methodologies, information navigation and conversational entity dialogue models. Information navigation goes beyond slot filling by not assuming that users more or less know what they want, and instead helping users discover interesting things about the world. Hard and soft constraints and multiple operators that may be clearly defined or fuzzy, like around or between, allow us to cluster and order the items, and thus allowing the system to do more interesting comparisons, suggestions, and other things. To facilitate information navigation, we chose the conversational entity dialogue model, an entity-centered model where, as you can see in the table, entities can be permanent or transitory and generally exist within the scope of the conversation. An entity may be an object or a relation, and CEDM will keep track of them, allowing the system to engage in more complex interactions and, of course, facilitate information navigation application. This is a generic architecture of the proposed model, where the encoder and decoder parts can be any type of model, and CEDM will keep track of the dialog state, objects and relations between them, relieving the decoder of this load and relieving the need for processing the input every time at every dialog turn. By explicitly tracking entities and relations, CEDM for IN can address the limitations mentioned above, as it is designed to handle complex dialog structures that in turn allow it to facilitate complex interactions that are grounded in short and long-term history, thus exhibiting in-depth knowledge and avoiding repetitive language. In this work, we have presented CEDM for IN, a new methodology for modeling conversational agents that stands in between traditional pipelines and end-to-end systems, can track objects and evolving relations between them, and can guarantee system behavior, and of course it's more easily interpretable than end-to-end architectures. As future work, we plan to prove our approach on well-known benchmark domains. Thank you for your attention.
Hi everyone, I'm Aishwarya Padmakumar and I'm here to present our position paper, Dialogue as a Vehicle for Lifelong Learning. Most machine learning applications follow a pipeline that looks like this. We design a task, collect an initial labeled data set, train a model, and test it on held out data. But in the real world, we may encounter test distributions that are different from the training distributions, that change over time, or that require a different task definition from what we started out with. To adapt to this, we would need to collect a new labeled data set for the new test scenario. An alternative paradigm is lifelong learning, where the model is designed to be initially trained on an initial labeled data set, and then as it goes through test phases, it collects additional labeled data for the same or different tasks, and the model is trained to incorporate these. Lifelong learning can make models more generalizable and versatile, adapting to concepts and tasks that are not predefined during the initial training phase. Lifelong learning is particularly relevant for robotics applications in environments such as homes and offices, where it may be difficult to enumerate ahead of time the objects the robot may encounter or the tasks it has to perform. In this position paper, we present dialogue for supporting lifelong learning as a new challenge area for dialogue researchers. Dialogue systems are in a unique position to perform lifelong learning, as by design they interact with users at test time. This provides a mechanism for collecting additional labeled data during operation. To do this, dialogue systems would need to incorporate active learning, identifying examples that are most likely to improve the model and querying for their labels as part of the dialogue. One framework for doing this is opportunistic active learning that incorporates locally convenient active learning queries into dialogues. These queries may not improve the performance of the current dialogue, but are designed to improve the expected performance of future interactions. An example would be a robot, when asked to bring a blue mug, may point to an object nearby and ask whether the label blue applies to it. The robot may also query for a different label that is, such as tall, that is not related to the current task, if that is more likely to be helpful in future interactions. We believe that this area presents a number of interesting challenge problems for dialogue researchers, including designing dialogue acts to collect new types of labeled examples. For example, a robot engaged in a cooking task may ask how a particular step, such as opening a can, can be performed in a different way, expecting a demonstration. Another challenge is collecting data sets and designing dialogue simulations to demonstrate new concepts being added at test time and providing correct answers to active learning queries. Another challenge area is prosodic analysis to identify emotions such as urgency, stress, sarcasm, and frustration to determine when it is appropriate to query for active learning. To learn more, please take a look at our paper or contact us with your questions.
We have a few minutes and we enter the phase where we do live Q&A for the late breaking reports and the position papers. I'm going to share my screen once again. Let's see here. So to access the to join the Zoom meeting so you can come ask questions. If you go to the Trello board and scroll to the right here, you go to session 4, RoboDial 2.0, and then scroll all the way to the bottom. Right here, the live QA session for position papers and late breaking reports is right there. Click on that and you have joined the Zoom live QA. So do that and we will let you in slowly. That's it for me. The chair for this session is Vikram.
Thanks, Casey. And yes, I believe we still have a few minutes until...
I can't hear you.
Or can you hear me now?
Wait, that's probably my fault.
Can folks hear me? Yes.
Yeah.
Okay, okay.
Yes.
Excellent. So let's perhaps give it a few more minutes. I just want to check that everyone's here. So while everyone's slowly trickling in, I'd like to reiterate that it's been a great session so far. Thanks everyone for participating in RoboDial 2020 as part of SIGDIAL 2020. And I think it's been a great session so far. And I'm Vikram. I am Vikram Ramnarayanan. I'm a senior research scientist at Educational Testing Service, and I'm also adjunct faculty at University of California, San Francisco. And I also happen to be the secretary of SIGDIAL. And I have the privilege of chairing at least this part of the Q&A session for late-breaking reports and position papers. As we all heard in the last half an hour, or perhaps before that, if you had a chance to view the videos, I think we've had a lot of really interesting developing work that I'm sure you have a lot of questions on, as well as potentially, questions that questions we may not get answers to right now in the position papers, but some interesting discussion points that the position papers raised. So what I'm going to do, since we have just about half an hour, we had originally budgeted half an hour for the Q&A. I'm going to try and see if we can sneak in an extra 5 minutes, provided all the authors are here, or at least someone from each paper is here. So let's see, is Thierry here? The author of the multimodal corpus? He may not, because it's 2:45 a.m. in France. So it's somewhat inconvenient for him, but perhaps I'll move down the list and see if, Nikhil, are you here?
Yep.
Yeah, okay, great. Ifra? Okay, Ifra isn't here yet, so we probably have to wait since two of the folks are not out here. I do see Alex is here and Raymond is here as well. I don't know if Aishwarya is going to be joining us, but...
hopefully she'll be here.
Great. So I guess we can open the floor for questions, simply because, we have people over here, so maybe we have to work out of order. Initially, I thought we'd keep about 15 minutes for the late breaking work and 15 minutes for the position papers. But we might, I'm also open to being a little bit more flexible depending on the questions people have and the directions that we choose to take this in. So with that being said, let me, since we are about a minute away from the 45-minute mark, perhaps we can just get started. Okay, and I see Ifra just joined.
Hello.
Hello, okay. So I believe that's a quorum, and Thierry may or may not join because of the time difference or the time zone he's in. So let's just get started. So let's start with the second paper, Nikhil's paper, since Thierry is not here. And I'd like to open the floor to any questions. So this is on the situated multimodal control of a mobile robot. Does anyone over here have any questions? If you do, you can either raise your hand and I can call on you, or please feel free to also just unmute yourself and ask the question. If there are no questions, I did have one, and I was wondering if you could talk a little bit more, Nikhil, about the delays and latency and how that affects the processing of the system and how you handle it currently.
Yeah, so I think there's a few points in delay. So there's the speech and gesture recognition, obviously. So the speech recognition is incremental, so it will recognize word by word, and then if there's a delay of, I forget what the time limit is, but half a quarter of a second or something, it passes the entire thing. And then the gesture recognition, it uses basically an intent module. So once it determines that a certain hand pose and arm pose is reached according to predefined heuristics, it will communicate an intent of, say, push left or point with the direction. The gesture recognition runs entirely on one computer. So there's really quite low latency with that. The most latency comes from communicating back and forth to the Redis server, particularly if we're using an external Redis server. So what we do, there's a couple of techniques that we use. One is for each channel has a specific Redis publisher. So no channel is being clogged up with other channels' information. So we at least maintain, it doesn't solve the latency, it at least keeps all the latency consistent. So everything should come back at the same time. And then we're currently working on techniques to speed up the interpretation. The robot is capable, or the underlying system is capable of handling things like asynchrony and interruption. So you could say, wait and interrupt the current action, and then it will say, paused, waiting for input, and then it will you communicate your next instruction, and it will proceed. You can what it can do is, we've set it up so basically, if the robot is saying something and another instruction comes in, then the robot will kind of interrupt its action and proceed. So it tries as much as it can to be proactive. And there, of course, there's the obvious pain points of, say, the Redis communication that we're working to overcome. So, yeah.
Great, thanks. I think Ifra had a question as well.
Hello, it was a great presentation that you gave, and congratulations on being an assistant professor. I actually wanted to ask you about the vision component, like in terms of like the hand, like for a robot to understand, like you're pointing, doing the finger and everything. Yeah. So how delicate was that vision component, and what were you specifically using? Yeah.
Okay. Yeah. So the vision component comes out of a previous project, sort of a different type of intelligent agent that we basically transfer a lot of the components over to this agent. There are, I believe it's an 11-layer deep convolutional neural net trained over approximately 8 hours of RGBD video data gathered from human elicitation studies. So these were human-to-human elicitation studies of the types of language and gesture that people use in construction tasks. So we basically took this construction task domain of gesture where you got, pointing, grab, push, the sort of iterated push, some of which you saw in the video, transferred it over wholesale to the robotics domain. The robot doesn't have grabbing. It has no grasper. It doesn't actually move things. So we basically retooled all the gestures to mean different things in context. So pointing is the same. But then we can use this sort of grab gesture to, currently it's used to sort of grab the camera, and then subsequent manipulations actually move the camera. So we're able to have these two different modes where I can swipe left, swipe right in order to switch the camera views. The gesture recognition largely focuses on hand position and arm motion, so hand pose, basically pointing, sort of blade, claw, and then the direction of arm motion.
And I had a follow-up question, but I'm not sure if you have time. I can ask it towards the end as well.
Sure. If it's really quick, you can ask it right now.
I'm not sure, but it was actually related to the fact that, for example, right now you point to a position and you use your language and the gesture to point to the robot that it should move there. But did you measure the accuracy of where you were pointing and where the robot actually thought it was going, and maybe it deferred? And do you think that in the future, do you want to incorporate clarification questions or something like that?
Yeah, we do want to incorporate clarification questions. So there's two angles to that. One is we could evaluate based on accuracy of pointing versus where the robot ended up. And then we could also maybe take that and use that to determine whether the robot should clarify if I'm pointing to, say, a location or an object, and maybe code in biases toward one or the other. That's the quick answer.
Yeah, thank you.
And David, I see your hand up. Did you have a quick question?
Sorry, I was muted. Yeah, just wondering if you deal with vague language at all, or things like even you have two, go to an object or go through or something like that. Do you handle that kind of thing where it might be subject to interpretation, how far exactly or where?
Yeah. So there are some defaults. So if I say go forward, it's basically go forward 1 meter. So there's some assumptions that are built into that, but you can also be more specific. And then if the robot encounters something, if I say go there and I put some location, and it say can't find a path, it might say, we could make it say, do you mean, propose another location perhaps, or like along this wall, or if there are two different objects, say, do you mean the red one versus the green one, depending on how it identifies as objects. So there is some handling for vague language, and we've done quite a lot of research on that in other contexts that can be brought over into this context.
Okay, we should move on in the interest of time to the next paper on grounding human-robot dialogue in environmental sensors to help the elderly. And Ifra's here to answer questions, so I'd like to open the floor to any questions for Ifra. And I see Aishwarya has her hand raised. Please go ahead.
Hi, Ifra. I liked your talk a lot. I wanted to ask you, so from the talk, I got the impression that the actual framework for detecting whether or not people have, done the task they were doing safely is not in place yet. Do you have ideas on how to set that up?
Thank you for such a good question. So right now, our main focus, since it's still a work in progress, our main focus was on the language component and doing grounding while looking at if we exhaustively look over all the possible scenarios, does our dialogue manager handle that? So that was the main focus. But in the future, we actually have thought about it. We have, so I'm doing this in collaboration with Momotaz Begum from University of New Hampshire. She actually works with a lot of like Alzheimer user studies and robots. So the way we are thinking of proceeding further is to involve real physical sensors, which are not just bounded to the robot sensors, that is the RGBD camera, but we are also thinking of incorporating smart home devices. For example, to see or check if a stove is on or not, maybe the vision component is still not there to see if it's on or off, but a temperature sensor can directly tell you, and it might even have like better real-time processing because that will be just a thresholding between the continuous sensor value that we are getting. So we hope to incorporate these different levels, different types of sensors and do it in real time so that we can incorporate those in our dialogue manager. So yeah.
Thank you.
I hope that.
Great. I see Nikhil also had his hand up. Nikhil, please go ahead.
Yeah. I think this is mostly because I was having some trouble hearing some of the audio in your video examples. So if I remember right, and correct me if I'm wrong, there was one where the person asks the robot for like instructions on a recipe. Is that right? And then the human asks them for something else, and then the human kind of walks away. Was that intended to demonstrate sort of two parts of the same task where the person sort of initiates the recipe and then maybe they walk off, leaving the stove burning, or am I misinterpreting what was going on there?
Yeah. So when I was making the video, I actually left the stove burner over there. So I went to pick it up. So it wasn't a part to show any feature of that. But yes, when the main thing that we wanted to show in that part was that even when the user is saying that I can do this task safely, the curry robot, if it characterizes, or the dialogue manager characterizes as a recipe task to be not that safe, the robot or the dialogue manager insists that I will monitor you, because in that way that will be better for your safety. So that's like the main gist that we wanted to show.
Okay, thanks. Thank you.
So Ifra, I did have a question more generally. So I'm wondering what plans, if any, do you have to test this out with actual elderly patients, simply because I suspect that some of the problems that you describe in this paper, as well as some of the advances, might have to be rethought a little bit, for instance, right? So for instance, the speech recognition, if people have dysarthrias and things like that, there'll be problems with the speech recognition module, and you might want to reweight sensors towards some of the others. So any thoughts on that?
Yeah, so basically the way we were thinking of doing this was that first we do a sort of like a simulation, which is on synthetic data, and have that in front of the elderly and collect a corpus, which is where we can actually analyze what actually are the real problems while dealing with the real user base, which is like elderly. And once we incorporate that, we do another iteration of our dialogue manager and incorporate those for our final version, where we can deploy it either in like for a long-term study or something like that. But I can imagine that this is not just one iteration, but a multi-iteration process for the paper. And this is just the start. So yeah, thank you.
Great, thanks. Any other questions for Ifra? I'm also trying to see if Thierry is here, but he isn't, unfortunately. So what I'd like to then do is perhaps move on to, if there are no other questions for the late breaking papers, I'd like to move on to the position papers and potentially at the end, open it up to people who might want to ask all the authors questions. So that five minutes or so at the end is conserved for that. So if that sounds okay, I'd like to move on to the first position paper, which is by Alex Papangelis and Stefan Ultes on meaningful grounded conversations with dialogue agents. And before I open up the floor, I did see, and I'm sure many others would have seen, a lot of connections, potential connections between this position paper and the following position paper on lifelong learning. So I'm pretty sure this is grounds for a very interesting discussion ahead. But with that being said, I'd like to open up the floor for any discussions. So if you have questions, please unmute yourselves and ask your question, or please raise your hand and I'm happy to call on you. And if there aren't any questions, I can start off with one of my own, which was, I was wondering what your practical plans were in this space. So you mentioned, talking about benchmark data sets. Could you elaborate a little bit more on those plans? Because I think this is a really nice framework, but it would be interesting to see how to actually implement some of these things, Alex.
Yeah, that's a good question, I guess. So we will start, with data sets like MultiWAS that have multiple domains and have, ontologies and things like that we can actually use to train the system. And then, hopefully take it to kind of larger data sets. I don't know off the top of my head right now, kind of my next steps would be probably MultiWAS, but any other data set that has some kind of knowledge API or something like that would be very good. And apart from that, what would be interesting for me would be, kind of constructing our own knowledge graph that represents the state of the dialogue, like entities and relations and all of these things in that space. and how can we refer to things that happened in the past, maybe in previous dialogues. So I think we mentioned that somewhere in the paper that it would be nice if we had longitudinal data with people talking to agents. So I know there are some kind of data sets, but I'm not sure, if they are enough or the annotations or something. So that would be definitely something that I'd like to explore. Having, like, say, a few users talking to an agent over a year or 6 months or whatever is feasible. And then, just trying to see how we can remember things, how the system can kind of adapt to that user and can understand, referring expressions and other things that are not explicitly mentioned, even in this dialogue and so on.
Great, thank you. And Matt has his hands raised. Please, Matt, to continue the discussion.
Sure, yeah. Hi, Alex, and I really enjoyed that, the presentation. I was just wondering, you talked and proposed the idea of information tracking, and I was wondering how you might relate that to the previous work that's gone on, like Larson and Traum on information state.
Yeah, I guess there are a lot of similarities. So what we were trying to do was try to, I guess, do two things, right? Have kind of a good symbolic representation, and that is the CDM part, which is mostly Stefan's work, and that, I guess, relates to the information state updates. But I guess maybe the difference is that it tries to view the conversation as a set of objects and relations, like, for example, we do in objective-oriented programming. And so by doing that, hopefully we can allow for the system to be able to understand relations that haven't been mentioned before. So maybe we can have a way of, treating values that we don't know, or even slots that we don't know, but relations is something that I haven't seen anywhere. So that's, kind of one of the motivations, I guess. Yeah, I think Stefan would be more appropriate for these to talk about the CDM, but that's kind of my understanding.
Just a quick comment. You may find research in ontologies relevant to this. I'm not sure, there's not a lot of recent work in dialogue looking at ontologies too much, but there may be something out there from maybe before the neural network boom that may have some insight on that.
Yeah, definitely. Yeah.
I see Raymond has his hands up.
Yeah, so I like the idea of having this intermediate representation that's explicitly symbolic with relations. Have you thought about how to use that information? And there's been a lot of recent work on graph neural nets. Have you thought about what particular types of graph neural nets might be appropriate to then interpret that graph of objects and relations?
Yeah, I guess that's a great question. That's definitely something that we are looking to do, but we haven't actually gone there to the point of, selecting a model and things like that. So definitely graph neural nets is a thing that we want to try. We want to try also more traditional baselines, and maybe even pre-trained, big pre-trained models, fine-tuned, and kind of see how, I guess, what's the pros and cons of each approach, maybe. But kind of early work still.
And perhaps this is a nice segue into talking about connections between the papers. So you mentioned one of the things that is deficient or that needs looking into as longitudinal data, right? And as in terms of this continuous improvement cycles, things like that. And so something like lifelong learning seems to be a very good candidate for this, of course, in general, but the challenge is always how specifically to adapt techniques from lifelong learning principles into this particular task. And so having seen the other talk, I'm wondering whether both you, Alex, and you, Raymond, or Aishwarya, have any thoughts on that?
Yeah, so I mean, in some of our work on trying to use dialogue for this sort of lifelong learning, we do assume there's some kind of ontology or task structure. I mean, we focused on fairly simple tasks like just retrieving objects based on description. So not too many different slots, but like, you can think of it as like, there aren't too many different slots, but it's a very large set of possible values which can be involved. And like what we have sort of focused on is like, okay, say you need a certain number of perceptual categories for a system to know to be able to ground these descriptions. Like we sort of want to be able to, we don't want to fix that set ahead of time, but you want to be able to identify new ones ahead of time. So like, it's sort of similarly, like I think in general, like there are many other situations where you may not want to have like your slot value set, or in general, like any knowledge base you're referring to fixed over time. Like even if it's something like a restaurant reservation task, like their menu presumably changes over time and things like that. So I can see that like there are many applications where it might be helpful to have a way to like update the knowledge base over time. And like depending on the application, you might want information from the users themselves or from, say, the business or person managing the dialogue system.
Alex, Ray, any thoughts?
Yeah, I agree, I guess. What we were trying to do was trying to say, besides the CDM model was to combine, I guess, CDM with another kind of paradigm that is not always slot filling, and even if it is transactional, that the user may not always know what they want, and that to shift it a little bit to kind of more complex interactions, right? So what if you want to do rehabilitation over 6 months, or if you want to design a tutor that is with somebody for a year? And so, having focused on that, of course, lifelong learning is definitely the next step. But we were kind of looking into taking the first step. How can we get out of the simple slot filling that, sometimes leads to systems that basically we don't do a lot of understanding, and we mostly do keyword understanding. So we understand what phrases map to what values and slots, and then, that's it. But there's an entire other world of systems that we can build, right? And even just, I guess, in industry, there's more complex systems, but in academia, there's not a lot of systems that can handle like operators that are not equals, right? And all of the other kind of operators. So, yeah.
Yeah, and this is partly extremely relevant for at least one of the topics of discussion I wanted to spark with Aishwarya and Raymond's paper, which was in terms of we don't have too much data of any given data set, but we potentially have a bunch of data sets and they're disparate. But then how do we leverage that for either lifelong learning or for multitask learning in a way that makes sense, right? Because each of these have different slots, and Alex and Stefan's ideas potentially talk to kind of bringing us to a common ground, but then still there's this gap we need to kind of almost bridge before we can actually do that. But once we do that, we can actually take advantage of having a large number of small data sets, if that makes sense, right, across the robot community in some way to kind of move this forward.
Yeah, that's true. In fact, in like our work so far, we've sort of done, like we've searched for data sets which have annotations that we can use to simulate an effect like lifelong learning. But it would be nicer if we can use more of the data sets we already have, because like in the work which we have done so far, we do require like a lot of annotation to like answer these information gathering queries, to like change the task structure over time. And so like we've used data sets like visual genome, which have a lot of things annotated. Now you can't expect to collect a visual genome for every domain where you want to have a dialogue data set. So it would be nice if we can figure out how to leverage like other types of annotations. So like in a lot of dialogue data sets, like the data you have are really just sample conversations. So like you sort of need reliable methods to like extract actually like in this case, I do see a lot of connections with Alex's work. Like you would need to be able to look at look at other dialogues and like extract some sort of structured knowledge from them so that you can like use that to maybe simulate new dialogues or like just in general be able to answer the kind of queries you would want to ask when training a system that's intended to say switch between domains or like expand its task definition over time.
I do want to keep an eye on the time. We have about 5 minutes left. And also want to make sure that if anyone else have questions, they get a chance to ask them. So I do see one person, Mayank. You have your hand raised. Please go ahead.
Hi, I have a question for Ifra, if that is fine to ask at this point, or has the time passed for that paper?
No, that's actually okay. Right now, since it's the last 5 minutes, I figured we could open the floor to questions for everyone. Please go ahead.
So something that we were working on also involved intervening conversations for the elderly population. So I had a few questions, which is, first of them is, with the agent that you had, like the physical robot that you had, was it like a sleeping Alexa kind of device, or did you have to manually turn it on? I mean, what is the method of invoking the device? That's probably the first question. The second question is, how do you intervene if something goes unsafe on the unsafe lines? Is it only time dependent, or is it something else that you capture? And the third is the data set that is being generated in this process recorded somewhere for public viewing and usage, or is it proprietary to your research?
Hello, thank you for the questions. So the first question was, so it is, I think, I'm not sure whether what you meant by Alexa, but the way you invoke is, it has a wake word, which is hey curry. So for this work in progress, I had to say hey curry, and then the sentence so that it knows that I'm actually talking to him and not mentioning curry in some conversation. But we are thinking, after looking at such helpful, the reviews for the paper were really helpful. And to incorporate those, we are going to think on the lines that the invoke word is something which is removed and it's more generic, but I still need to work and think about that. The second thing, to discover whether the task is safe or not, it is so for now we haven't incorporated the real world sensor, but we look exhaustively at all the sensor values, and the sensor state values that we look at is not only time dependent, but it is also about like the knife usage and the stove usage. So if we think that maybe in the future when we incorporate the real world sensors, if the computer vision model is saying that okay, the hands are trembling while using the knife, so maybe it's not safe for the elderly, or if after the step has been completed, the stove is still on because the home device temperature sensor is saying that it's still on, we will say that it's still not safe. So we hope to incorporate that. And the third question, I've forgotten, about the data. So right now, since we use synthetic data and we still, like, this wasn't data which we collected by actually talking to the elderly. And we are going to use the synthetic data to actually curate a corpus of the elderly, and we hope to make that public for everyone. So yeah.
Right. So if I understand that, thank you very much for the answers, first of all. If I understand that correctly, that means that you have a data structure of some form which captures the sensor values, and then there is an NLG component which is combined to generate a human form of sentence.
Yeah, so right now we actually, you can think of it as we have stored all possible values, that sensor values that it can take, but they're only binary outcomes. So we have reduced the complexity of like the real-time processing as well. And we need to incorporate all of that real-time processing in our future also. Yeah.
All right. Thank you very much.
Yeah.
Thank you. And thank you, Ifra. We have about a minute left, so I guess Matt gets the honor of asking the last question of this Q&A session.
It's a question for Aishwarya and Ray, which is, for lifelong learning, there seems to be a spectrum in terms of agency and scope, right? And so do you think it's more important to prioritize the hive mind doing a lifelong learning or an individual agent?
I think we're probably likely to see more benefit from like a hive mind style lifelong learning, because especially now that we're using these deep learning models for a lot of things, like we've sort of seen in some of our experiments that you can't expect these systems to improve a lot from like, say, a small number of examples which one person is likely to give. So like there are many applications, like especially I can think of things like home robotics, where it would be very frustrating for one user to have to train the robot to do some kind of zero-shot recognition. Now, if we got better at really doing zero-shot learning or one-shot learning, then we could do sort of a like personalized update. But I like a lot of the recommendations which I've suggested in our position paper are more in like the hive mind kind of setup.
Yeah, certainly that's always the way that I've looked at it. I remember in our earliest conversations with Jesse, who Matt knows quite well, it was always the idea that eventually we want to have a whole army of similar robots in homes all over the world. And then that all their users are contributing training data every day to make them better and better. And it's frustrating though, because of course we don't have that army of robots over the world, but eventually we will. And then they're going to learn like gangbusters from all the users that they're interacting with.
Right.
Great. Thank you, everyone. We're a minute over, which just goes to show how many questions there were and how interesting and discussion worthy all the papers were. So thank you again to all the authors as well as all the discussants. And hope you enjoy the rest of SIGDIAL. I think this has been an amazing RoboDial so far. I think this is the last session of RoboDial, and I think it's been excellent. And hope we continue to do more of these. So with that, I will turn it over to Casey to take us away.
Thank you, Vikram. Yeah, this is it for day one. I know some of you have been with us the entire time. I appreciate that. Some of you, just based on time zones, missed half of it or even had your sleep right in the middle of it. But that's the nature of it. Just so you know, I'm going to share my screen yet again. Just so you know, all of the live stream recordings, or all the live streams have been recorded and will be posted in each day's Trello card here on the left. So for example, today we had 3 live streams, one from this morning, that was the keynote and session 1 plus the QA, that's here. And then the second one was session 2, and then 3 plus the QA, that was here. And the other one is happening right now. So when this is done and finished processing, I will also add it. So each of these Trello cards will have the live stuff that took place that day. So anyone who wasn't able to stay with us the entire time, for whatever reason, you can go back and watch anything you want to, live QAs, everything. I also wanted to point out I got one breakout discussion that was recorded, the natural language generation. Shireen Orabi was the leader there. So that is also posted. You can, if you're interested in natural language generation and the discussion that happened there, that video is there for you. And if any other discussion leader had a video, please let me know and I can add it to the SIGDIAL 2020 YouTube channel. But that's it for now. The next session 5 starts in a while. So you have time to take a break. And once again, welcome to SIGDIAL for 2020. Thank you all for your participation today, and I look forward to more discussions when the next session starts.
Thank you for organizing.
Thank you.
Thank you.
Thank you.